Buongiorno a tutti.
Good morning, ladies and gentlemen. On behalf of Italian Exhibition Group, I'd like to welcome you to this edition of VICENZAORO Gold. This is a record exhibition, 1,300 companies in 15 pavilions, which are showing to the world the made in Italy products and what best companies in the world are making. The program of events is also very important. I'd like to thank Legor Group for the long-lasting collaboration and for offering a very important program to have updates and information on technical issues. So enjoy the day.
Buongiorno a tutti.
Good morning, everyone. I would like to thank the participants to the 18th edition of the Jewelry Technology Forum, and my warmest thanks goes to the speakers and all those people who collaborated to the organization of the event. We'll have experts from the jewelry, silver, and fashion world. They are entrepreneurs, consultants, engineers, designers. We have a very interesting agenda for the day. We'll hear about many different topics. It's important to have a high number of speakers because they are the backbone and the nourishment of this symposium. It's like exchanging energy and culture within the world of production and technology. This is very helpful because that can help our collaborators in-house to work in the projects which can be helpful for companies to grow. First of all, I'd like to thank Eddie Bell, who is the founder of the Santa Fe Symposium, who held the last edition last year in Albuquerque. I also would like to thank Chris Corti, who is sitting here with us. He has been with us throughout these 18 years, offering great support and help over the years. I also would like to thank IEG, the Fiera di Vicenza, for the commitment. This is the ideal venue for the meeting, allowing great visibility to technology in the T-Gold section, which is one of the most important events in the industry in the world. I also would like to thank the Scientific Committee of Legor for organizing the meeting and supporting the speakers. My wish is that JTF and the papers could contribute to the development and the improvement of knowledge and skills within the company, that they can become the nourishment of every project. You'll have the opportunity to exchange ideas and to talk to the speakers. The idea is to convene people here and offer them the possibility to talk also after the meeting. All the presentations delivered over the years can be found within the website www.jtf.id. This is a sign of the commitment of organizers to offer the opportunity to read all the papers which are presented during the symposia. Allow me to present the agenda. Dr. Jörg Fischer-Brunner will be the moderator of the morning, and then engineer Andrea Friso will do that in the afternoon. Enjoy the symposium. I hope we will hear important information so that our companies could grow even further. Thank you very much.
Thank you, Massimo. Good morning to everyone. Yes, I have the pleasure to moderate the morning session, and I think we have like 100 registrations, so we expect a few more people to come in. And also we welcome a couple of attendees that are attending online, watching the presentations, I think, on YouTube. So this is a forum, and a forum is a place to meet and to discuss. So please write your questions or your remarks down. I think in your folder you find some paper. So during or after the presentations, you can write down your remarks and questions and pass them either to the speakers or to Andrea, the organizers, or to me, and we will pass them to the speakers. And then at the end of the morning session, we will go through the questions together. Yes, we have a couple of presentations. First of all, there's a block on not so technical, but more on financial and economic aspects of the jewelry industry and trends. Then we become more technical. We have an introduction into the digital aspects of the jewelry industry. We will go into an overview presentation on additive manufacturing, and then go further into the details of one particular additive manufacturing technology, namely the binder jetting. So that's the morning program. I think we can start with the first speakers. We have two speakers sharing a presentation on financial and economic trends. We have Sara Giusti and Daniela Corsini. So Sara Giusti holds a master degree in economics, obtained at Cattaneo University in Varese, Italy. She's an economist at the Industry Research Office for Studies and Research Direction at Intesa San Paolo Bank. She's involved in research regarding industrial economy, in particular on sectors related to the fashion industry and also on the Tuscany and Umbria regions. Her speech today offers insight for the Italian goldsmith sector regarding its positioning and the main strategies that can be adopted to guide it. Yes, so welcome, Sara.
Grazie, ringrazio Legor per...
Thank you very much. I would like to thank Legor for their kind invitation. In my presentation, I shall try to share with you our most recent estimate on the industry. And let me say that in 2021, the goldsmith industry grew importantly. In 2021, there was a rebound that was just physiological after the drop that was experienced in 2020. Well, in 2022, the growth is certainly still there, which is a sign of a structural growth in the industry. This comes out even more evidently if we compare goldsmith industry with the fashion industry. On the right-hand side, you see that the goldsmith industry and custom jewelry grew by 30% in the first 11 months of 2022 when it comes to manufacturing percentages, whereas the fashion industry is still lagging behind, and it is basically stable as the rest of the manufacturing industry. This is happening at a time of stable demand for gold jewelry. At the beginning of 2022, based on the data of the Gold Council, the global demand for gold jewelry was equal to 1,500 tons, with a growth by 2% vis-a-vis 2021. And you see that in terms of markets, there are quite reassuring results in India, especially in the Middle East and in Europe. Well, actually, in the Russian market is certainly lagging behind because of the war, and India is still suffering because of the zero COVID policies they had adopted. We still have a good result as supported by the demand at the festival in China and by the growth in the number of weddings. There's certainly a great competitivity on the foreign market. There's indeed a greater trend towards export and good results that have been recorded when it comes to export again. This is something that is pointed out by the chart on the left, where we've compared the trends, which sees an important growth on value-wise by 30% vis-à-vis the previous year and by 40% vis-à-vis the year before the crisis. This is the data that are available up until September 22. And you see that quantity-wise, the growth is still relevant with an increase by 16% quantity-wise vis-à-vis the value of 2019. We also wanted to share with you a middle-term vision. So we wanted to show you that this is a process that comes from quite a long time. Here we are looking at the last 30 years, and you see that this bounce and there's a stability basically is the result of repositioning in the market. That comes, again, that dates back from a long time. Some 7 billion were the export for 2021. Again, this is the result of the repositioning of the industry vis-à-vis the higher end. And you see that main markets record growth. Certainly, US are doing well. The US are becoming indeed the first reference market for our experts. An important growth has been also recorded towards the Emirates, and then we've seen other markets that are growing that are certainly important in the luxury industry, as Switzerland, for example. And Ireland is another market. There's been important growth since 2020, but here again, this should be seen because a number of goldsmiths have used this as a hub, but there are a number of multinationals that are targeting the Irish market. You should also recall that the Irish market has somewhat replaced the import it used to have from the UK with import coming from our country. And the export market for Irish products is China. In relative terms, not just looking at value, you see that Italy is growing importantly also in terms of market shares. Between 2012 and 2021, the market share for Italy grew by some 3 points. We stepped from 3% to 8%. And this has been made available also by the growth that was recorded on the US market. In this case, we looked at the weight that Italy has on the import of jewelry in the US, and you see that basically we shifted from 7% in 2009 to 12.5% in the first 11 months of 2022. This is very significant because of the role of the weight that the US play in the world of gold jewelry, of the top of the range gold jewelry. To further describe the development of this industry, we should also refer to the different districts. Indeed, at our bank, we look at different districts. We look at the Valenza district that account for some 80% of the exports. And you see that these are three districts, Valenza, Vicenza, are growing importantly, somewhat in the range of 30%. If you look at the pre-crisis value, you see that we are still lagging behind, especially when it comes to the Valenza district. But there again, we should recall that these data are expressed with reference to value because we don't have any other data. So there could be an underestimation there because it might not include the real trends. So this is the overview of the results that have been achieved in the industry. And we'd like to focus now on our expectations. Well, 2023 is going to be a year of change. We actually expect some kind of slowdown in the well-developed countries. At the end of 2022, we still have a lot of pressure as exerted by inflation. The inflation that is recorded is something that exceeds the one that we have seen in the 80s. But there are risks out there that we should pinpoint. First of all, inflation again. The development of inflation is quite remarkable, especially in view of the monetary policies that central banks are triggering. Monetary policies are going to make necessary to curb inflation. We're faced with the two types of different inflation in the US. The inflation is supported by high demand, so monetary policies have more direct efficiency. In Europe, inflation is imported as connected to the oil shock, the energy shock. So the effect of the monetary policies are less effective. Energy is another important issue to consider. Thanks to the weather conditions, we've been supported, we've been helped in terms of curbing consumption. But this is an issue that we should consider again, because the stock are going to be piled up in the future, and we have to look at and see what is going to happen on the energy market. There is another important subject, and that is the geopolitical risk as connected by the war between Russia and Ukraine. So the intensity and the length of the conflict is certainly to bear importantly on that. Now, looking on the US, our expectations are of important change in the US. Our expectations indeed are somewhat connected to a technical recession, which we believe is going to be of little intensity and little duration. In terms of monetary policies, we believe that there's going to be a change there as well. As far as Europe is concerned, while the situation is a bit more complicated, Europe has been more affected by the energy shock, something that has not impacted on the US cost-wise. European governments have supported companies and families to tackle the oil shock, or to the energy shock, so as to try and reduce the effect that families and industries have to bear because of the energy costs. In terms of monetary policies, we've seen that the European Central Bank certainly has some little effectiveness. The discount rate is somewhat around 3.25%. Let's look at the data for Italy now. 2022 has been certainly bright for Italy. In 2022 has benefited of the good results in the manufacturing industry, the building sector that has been also supported by tax incentives that have been granted by the Italian government. And the good trend in the manufacturing industry can be recorded, especially looking at the rest of the European countries. In this chart, you see the turnover vis-à-vis 2019, and you see that there's been a rebound in 2020 and with a growth in 2022, something that was unexpected if compared to other European partners. This means basically that our entrepreneurs have been extremely resilient. Tourism has certainly boosted these good results. These are the results coming of our survey that we have carried out. We have interviewed a number of observers as to what they were seeing about 2022, especially when it comes to Italian tourist industries. And you see that half of the respondents were expecting to go back to the situation before 2019, which is evidence of the fact that a number of tourist destinations are actually proving to be resilient and have yielded very good results in 2022. As for 2023, well, we believe that we're going to expect two different situations occurring. At the beginning, we're going to see a slowdown. You see that there might be a technical recession, but in the second half of the year, thanks to the investments being made by, thanks to the National Plan for Resilience and Recovery, and then because of inflation, we're going to grow again. Overall, as for 2023, the average growth is going to be 0.3%, which is going to be better as from 2024. In 2024, indeed, we expect a growth by 1.8 as an average again. Now, we should connect these expectations also, or we should connect these forecasts also for the gold jewelry industry. Together with the Club degli Orafi, we've carried out a survey. We've asked companies whether they were expecting to see a growth on their turnover for 2022. Interesting enough, as you may see, there's a percentage of a growing company through the different editions of the service that we've been carrying out. And you see that at the latest edition, at the latest survey, which was carried out between February and January, the number of companies who are expecting to see their turnover growing is growing, and we've gone back to the beginning, before basically the conflict had broken out. So 22 actually has certainly been a very good year for the whole industry. As for 2023, forecasts are in line with what I said earlier on. So the business community in this industry expected to see some kind of slowdown. This slowdown is going to affect the home market, most specifically. We have indeed we measure very good trends for exports. The whole market certainly has to bear the burden of inflation, which is going to eat out the purchasing power of consumers for products that, of course, are not necessary products. There's another aspect that we're trying to identify, and that is the capability to see whether there has been a loss of competition vis-à-vis other manufacturers in the rest of Europe. This has been what we have searched for in our survey. We see that the main competitors in Italy that are the other Italian manufacturers and European competitors. So this basically tells us that the top of the range is most interesting for the majority of businesses in the industry. Competitors usually are not perceived as the main competitor. The national competitors are not considered as the main competitors in other industries. But in this industry, indeed, they are perceived as such. What about the difficulties that the industry has to come to terms with? Well, again, in our survey, we see that the business community perceives that the main difficulty has been identified as the lack of labor. So skilled labor apparently is what hits the industry worst. The second, there's a concern about the availability of raw materials. If we nearly all of the companies basically suffer from the lack of skilled resources, because again, the top of the range, of course, requires a very skilled human resources. We looked at the responses we had obtained at the end of the year, and you see that we shifted from 27 to 51% of the companies perceiving that the lack of skilled personnel is perceived as a great difficulty. As a matter of fact, the management of prices of raw materials is perceived not as much as an emergency as was said at the end of the year. When it comes again to raw materials, I think that my friend Daniela Corsini should take the floor and speak more to for that subject. Good morning, ladies and gentlemen. Thank you.
No
So
problem.
Daniela Corsini holds a master degree, cum laude, in economics, statistics, and social sciences at Bocconi University in Milan, Italy. She started her career in 2006 at Horizon Capital SA in Luxembourg as portfolio manager focused on equity funds for emerging markets. In 2011, she started her collaboration with Intesa Sanpaolo Bank in the research department, where she manages macroeconomic researches for commodity markets following energy, agriculture, industry, and also the precious metals sectors. Since 2011, she's part of the CFA Institute. In her part of the presentation today, she focuses on precious metals prices under the influence of several factors such as monetary and currency aspects, as well as economical conditions of the most precious metals consuming countries. Now your stage is open for you, Daniela.
Thank you very much. Buongiorno a tutti, grazie.
Good morning, ladies and gentlemen. Thank you very much for organizing this meeting and for having me on board. I shall be talking about raw material prices, and I shall be talking about our forecasts for 2023. In this slide, you see that I refer to the oil price. An extreme volatility has been recorded over the past year. We shifted from over $2,000 on March the 8th, 2022 to a minimum of $1,615 an ounce in September 2022. So these important fluctuations are something that is quite unparalleled, refer to the different forces at play when it comes to precious metal prices and gold price in particular. What is most important, I believe, is that the US monetary policy. There's indeed a strong correlation between the price of gold and the interest rates in the US. The higher the interest rate, the lower the price of gold. The stronger the prospect for slowdown in terms of increase of interest rates in the US, the greater the price for gold. These fluctuations basically have been witnessed throughout 2022, so the correlation with the US dollar has been the main driver throughout the year. The American dollar is obviously better appreciated when the interest rates are higher, and is depreciated when the market expects that the difference between interest rates in Europe and in the US is greater. So we expect that in the next quarters this correlation is going to play a very important role. Let me add that there are other factors at play when it comes to the price of gold in 2022, and that are still going to play a role in 2023, apart from the correlation that I've been referring to earlier on between the price of gold and dollar. There's the main risk being geopolitical risk. Indeed, the peak that was recorded in March was caused by the war that was perceived perhaps as even correlated to high risk involving a greater geographical area, with the gold again ranking highest. Then there has been a collapse in cryptocurrencies. Cryptocurrencies have been perceived as an alternative to gold in terms of a refuge, shelter, good. But you see that again, after the collapse of cryptocurrencies, now gold is the most important shelter good. In 2022, something happened that might not happen in 2023, and that was the anomaly in the financial markets. In 2022, we saw a collapse of both of the security market and of the share market, something that has never happened jointly in the past. Usually, this is not the case. It only happened in 2% of the cases over the past few years. So this double collapse of both the shares and the security market led to an ever-growing number of businessmen considering gold as the assets where to invest. Here you see how different and diverse the demand for gold is. Many other drivers are pushing people to buy gold. Central banks have been acquiring gold as well. You see that there's been growing demand. It shifted from being 7% of the overall demand for gold in the first quarter of 2022 up to 39% in the global demand for gold in the third quarter of 2022. A devaluation of the US dollar has been recorded, coupled with the geopolitical risks, have led to central banks to buy gold so as to diversify their portfolio and to hedge against the depreciation of American currency. So central banks are certainly going to buy gold for a long time, and especially emerging central banks are going to show a greater interest in gold. As for ETF, well, you see they have contributed to volatility. Indeed, they shifted from being equal to 20% of the global demand to releasing gold in the third quarter of 2022. Here you see that throughout the year, apart from the very last month, there has been a correlation between the price of gold and the volume of gold, as pointed here in orange, as held by ETF. There has been a rebound in the share market and the security market at the beginning of the year, reversing the trend that was experienced in 2022, led financial investors to prefer buying shares and security, neglecting gold. But we believe that this correlation might change over the next few years. In this chart, you see that there are other investors, money managers and hedge funds, unlike ETFs, are much more interested in following the price of gold. So this part of the demand certainly is very much interested in the prices of gold. Here you see what we expect for the future. So there are a number of conflicting factors to be considered, but we expect that fair value for gold in 2023 should be equal to $1,830. $1,830. Gold hit $1,930, but we believe that this price has been supported by two good expectations on the monetary policies of the US. So we believe that we're not going to see a reduction in the interest rates. So we expect that the price of gold is going to be slightly lower, and we expect an average of $1,830 for gold. Obviously, we have to keep an eye on inflation and on the war between Russia and Ukraine. Here you see that ETF position have been following the trend in gold, you see that basically there is a very positive correlation between ETFs and gold. So there's a strong correlation between the price of gold and the price of silver, and we expect that silver is going to remain stable over the next few months. Unlike gold, we believe that silver is not going to lower a lot. Gold is perhaps a bit higher in price that is going to be, but the silver will remain unchanged because there is an industrial demand for silver, especially for the technologies leading to the green transition and the solar panels industry. So we believe that the price of silver, again, will remain unchanged, some $23 per ounce for the following year. Now let me refer to palladium. Palladium is impacted by two issues, Russia and the automotive industry. Russia, because you know Russia is one of the top producers for palladium, so there's been a peak in the prices in March that was caused again by the fear lest that the palladium availability would be reduced to zero, but for the time being this has not happened because palladium can be sold freely from Russia, so this risk again turned out not to be one to be considered. And then we also have the automotive industry playing an important role when it comes to palladium, especially so for components of green engines. So we believe that the car industry is going to have a growth, and so we believe that palladium may appreciate over the next few months. As for platinum, we believe, as was the case for silver, that the present-day prices are going to remain unchanged, $1,100 for 2024 and $1,000 for 2023. Palladium is better coordinated with financial flows. It has recovered a loss is experienced. Here you see estimates for in terms of euro per grams. 52.2 is the price at the beginning and of 2023, and 50 is going to be the price for 2024. This obviously correlates with our estimates on the US dollars. Our colleagues that are following currency changes expect that there's going to be a reinforcement of the dollars with a stabilization at the end of 2023 throughout 2024. Our presentation are available on the website of the organizers. Subsequent updates are certainly going to be available also on the São Paulo website.
Thank you very much, Daniela, and again to Sarah for both of you for these interesting presentations. Just remind some of you who've been entering later, please write down your questions and your remarks, and we will have a question and answer session at the end of this morning session. So please pass your written down papers to either me or some of the organizers. So we are becoming a bit more technical now, starting with a presentation on phygital jewelry, and I guess we are all interested to learn more about phygital. From Beatrice Rosato. Beatrice started in 2020 as a PhD candidate in design at Politecnico di Milano, Italy. She actually works as a designer at Misani Milano, where she has the creative direction of shootings for jewelry collections communications. She's also a teacher at Poly Design and Cologne Foundation in Milan on graphic design, and has signed several publications on digital technology in fashion and jewelry. In her presentation, she is focusing on the relationship between digital transformation and the world of jewelry, and in particular on dematerialization in the contemporary context of products, services, and experiences. Starting from the changes of digital transformation and reviewing the multiple contexts of contemporary jewelry, we will see an analysis on digital technologies and tools with their applications among the real and the virtual world as they reach new generations. So, Beatrice, I hope you are there, and please start with your presentation.
Good morning. Good morning, everyone. Can you hear me?
Yes. Yes, we can hear you.
Okay, can you hear me?
Yes, we hear you very well. So
okay, perfect. Thank you. Good morning, everyone. It's really a great pleasure for me to be here. Let me first thank all the organization for the invitation. As anticipated, I'm a PhD student in design at Politecnico di Milano, where we are studying the effects of dematerialization of the fashion system, and in particular, innovative methodologies for the design of digital artifacts in relation to the body between physical and virtual landscapes. Today, I want to tell you about the latest trend, let's say, that the digital transformation has brought to the world of jewelry. And how a progressive dematerialization of products, processes, and services has taken place. Today, we hear more and more about digital fashion, a term that is really difficult to define, and it is not new, as we may think. In fact, the term digital fashion was firstly introduced to the fashion industry in general at the beginning of the 21st century, with the rise of the e-commerce. Then, with the development of 3D and virtual technologies, the definition has expanded to refer to any kind of fashion concept that are integrated with experimental technologies in clothes, accessory, and jewelry. Let's think, for example, to 3D printing or body scanning or virtual design. However, is in the contemporary context that the definition has expanded a lot more thanks to the entry of brands into the metaverse, acquiring more and more interest. This is, of course, an evolution where COVID-19 brought an undeniable innovative boost, but which began even before the pandemic. In fact, we see how before COVID, prior to COVID-19, substantial transformations were already underway in the fashion and jewelry system. That were radically changing the shopping experience and the relationship between the product and the consumer. Already mentioned before, e-commerce marked the very first dematerialization of the product, carrying the consumer to an online platform, so an online interaction with the brand itself. Then social networks, of course, have shortened the distance between what is the brand and the consumer, starting to widen the pool of people that the brand could reach. And of course, we have the technology and the digital in general that began to enter the product itself by introducing, for example, wearable technologies, and increasingly connecting the consumer, the object worn, and the digital environment. Or, for example, let's think about 3D printing and jewels that are created with the help of algorithms. Here you can see the example of nervous system that, thanks to an algorithm, can create the shape of their jewel that are then 3D printed for the end consumer. So we are witnessing a sort of co-creation of the artifacts that is generated autonomously by the machine, but then is customized thanks to the role of the designer and also of the end consumer. All this transformation were already underway, as I was saying, before COVID. As we can see here in this graph that is taken by the 2018 reedition of the State of Fashion, which reveals a really strong online presence of the consumer shopping habits. Of course, making a virtue of necessity, it is undeniable that how COVID has accelerated the digitization of fashion, and 2020 may be remembered as the year in which fashion retail made a definitely shift online. A change that, of course, has increased the interaction between the consumer and the digital medium useful for reaching the product and the brand. Such as, for example, if you think about all the great interest that nowadays brands have for gaming platforms. What we are witnessing, of course, is a change in consumer behavior, but also a change in the value that the object itself can communicate. The example that you see here is the iridescent dress by the fabricant. This is one of the first, let's say, creative factory of digital object, which even before COVID has understood how digital could reduce fashion waste. So objects are not don't physically exist, are not produced physically, but are made only digital and can be used as social filters. So let's say that digital entering the world of fashion brought like three changing in fashion. According to Philip Kotler, digital has led to this particular three change, from individual to social, from exclusive to inclusive, and from vertical to horizontal. So we are talking about communities in sense of social sharing of values. From exclusive to inclusive, so the inclusive features of digital environment, and then the omni-channel solution that an horizontal point of view can give. I would like you to focus for a moment on the world of fashion and luxury, of which jewelry is certainly an important segment. Are these conflicting values for them? If we think of fashion, but above all of jewelry, there has always been a strong importance to the physicality of the object. The value that the physical object can produce is one of the main characteristics that brands, for the brand success, for these exclusive features that they have. This is why initially there was a sort of refusal by the luxury sector to invest in digital processes. And in fact, they were probably the one that has the greatest delay in entering, for example, e-commerce. But today, of course, as I said before, almost 80% of luxury sales are influenced by digital. So it is something that brands cannot avoid anymore, to enter the digital sphere and starting controlling also this medium to reach the customer. What is interesting is that the features of digital and luxury are really different. If luxury lives in the name of exclusivity, for example, digital is completely inclusive. Luxury selects its audience and makes inaccessibility a sort of pillar of its existence. Instead, digital is aimed to a wide audience, and it is easy accessible to anyone. So we have on one side digital with an intrusive and open context that contrasts with the traditional closure of luxury. What is happening is precisely a democratization of luxury and an attempt to maintain the same values that has always been communicated in the physical, even in the digital context. Let's take some example. Think about exclusivity in physical fashion and luxury. Let's think, for example, of the presentation of Bulgari's new high jewelry collection, like the one, for example, here we have Magnifica. Like fashion shows are like reserved for a controlled circle of guests. In the digital world, the audience is widening. Here we have Cartier's Clash Unlimited collection that is created in collaboration with Dressed. Dressed is an app, digital app for creating outfit where the consumer himself or herself can become the architect of an exclusive look with the Cartier jewels. Or, for example, craftsmanship that has been and remains today the lifeblood of precious and non-precious jewelry. But of course, digital space opens up a new creative solution. Here we have an example of a New York-based artist that realized this project to make a sort of case against the manufacturing scarcity of diamonds. We can see that he created a limited set of 100 unique digital diamonds. And the digital artist links the price of those digital diamonds to that of the diamonds in the real world, debating the concept of value between physical and digital product. So you can see how the gems that are one of the main features of the craftsmanship also of the physical jewel can become a creative possibility and also to debate on sensitive concept in the digital sphere. Another value of luxury is certainly the authenticity. So the idea, the guarantee that the name of the brand or an authentic model can confer. As here in the example of the Hermes, the Birkin of Hermes. I brought an accessory and I will explain later why I choose especially this bag here and not, of course, a jewel. First of all, we need to say that digital takes authenticity to a new level with, for example, digital certification that are obtained thanks to the blockchain or that gives, of course, also the possibility to trace the production chain for a more sustainable approach to the product. But not only this. I showed you the Birkin earlier, just to reflect on the creative possibility of digital. These bags were created by Mason Rothschild, that is a digital artist who made use of the Birkin model to explore different creative solutions in the digital environment, selling them, of course, for millions of dollars as NFTs. Hermes, of course, then sued the artist for misuse of the bag's names by also distancing itself from the artist's works. Legal issues aside, it is undeniable that digital opens the door to material and formal experimentation that would not be possible or sustainable in the physical world. For an audience that spends a lot of time traveling, interacting, and communicating digitally, harnessing the creative value of intangible design can deliver, of course, an added customer experience and values. Despite the extremely different context, in fact, there are many opportunities that digital can offer. For example, from a selected audience, we can have younger and expected target, and this horizontality, the omni-channel solution. From high craftsmanship, of course, we can have artistic collaboration and less prototype waste. The authenticity can become digital certification and creative possibility. And all in all, we have from physical experience a sort of digital immersion. Keeping this in mind, I would like to present you some examples of how the products, processes, and services in jewelry have changed with the advent of this dematerialization. We define dematerialization as that, like the progressive reduction or the completely disappearance of the materiality of the object. As regard product dematerialization, of course, NFTs have certainly been the most explored novelty by brands in recent years. Those are unique crypto assets whose authenticity and ownership are verified on blockchains and are, of course, both sold and in exchange in the metaverse, often with cryptocurrency. The NFTs make it possible to transform the concept of collecting, transform it from a physical tendency to an intangible one, where exclusivity is given precisely by the rarity of these artifacts that is also combined with their feature of having a unique certification of their kind. For example, Tiffany has introduced recently the NFTF, their digital NFT that is closely connected with the CryptoPunk digital community. Thus also limiting the consumer it addresses. CryptoPunk owners can access the NFT website to purchase a pass, which will be, of course, stored in the blockchain technology. Then those passes can be then exchanged for custom-made charms that you are seeing here in the presentation, which will be designed at the Tiffany Innovation Center in New York City. Each pendant is a jewel, of course. It will be crafted in 18-karat rose or yellow gold, contains several gems and diamonds, and also has been designed with a special chain module that remind us to the shape of the pixels. So you see that the connection with the CryptoPunk community limits the access and gives this exclusive characteristic also to this NFT. Bulgari instead underlines the, let's say, exuberant and audacious characteristics of its nature, creating beyond wonder. That is a digital necklace that wraps up around the body of the wearer. It is made with like stones and colors that probably would not be found in nature. So Bulgari focuses on the impossibility of the object and on this immersive experience of digital storytelling. Digital product with or without certification becomes a social sharing tool. As the many virtual filters that have grown during the pandemic testify. The body, adorned by these moving jewels, becomes a canvas upon which the designer or the artist can place their creation. For example, here we have Ines Alpha that modifies the magazine covers by adding elements in motion, such as social filters. Or again, Sunny creates a filter for the rubberized collection to let the earrings be tried and shared immediately via social networks. The interesting thing is the relation with the body. You see how not only the object itself is rendered, but also the hairs. I think this is a clever way to remedy the visualization problems that often emerge with this kind of digital creation. NFTs and filters, of course, become an innovative expression of the contemporaneity, like the Mars glasses designed by Pedro Guetz that are made of glass, and is a filter that allows the owner to digitally wear them during video calls or game streamings. Or, for example, the Sozzani Foundation, that was one of the first examples of exhibition in the metaverse, that in collaboration with Taylor Ventures introduced these works of Chris Russ, an artist, that creates a set of jewelry specifically for this virtual exhibition that could be accessed through the app Dra6 and worn, of course, in augmented reality. Then the dematerialization of processes brings out two important changes, we can say: the 3D prototyping and the digital design. 3D printing is now a widely used medium and travels hand in hand with digital production, allowing the tangible realization of the digital designed product. In particular, it is really interesting to note how these two technological innovation can give rise to storytelling and exclusive customization of the jewel itself. The example that you are seeing here moving is a digital jewels by Love and Robots that moves according to the weather condition of a given place. So the jewel is conceived as a bearer of a memory of a place, that can be programmed to move according to the wind that was present in a chosen place. So imagine to travel to Rome, and then you want to fix that particular moment in a jewel, depending on the wind that was present that particular day. The jewel can be taught to move according to the wind situation of that day. The interesting thing is that then the object can be stopped in a configuration by the customer and will be 3D printed to give to the customer the physical jewel. A second example of process dematerialization are the crypto cameos by Andras Cognamiglio. Here we have an artisanal tradition, that is the carving of the cameos, that is completely reinterpreted in an irreverent way, we can say, in a completely digital collection of NFTs, with like a precision of detail that is challenging also the skill of the craftsman's hand. Or again, we have the Genesis collection by Dolce & Gabbana that introduced 3 pieces of eye jewelry, including this impossible tiara. That is a crown that is impossible to make, as the precious stone used don't exist in nature. As with Bulgari and the digital diamonds, the gem extraction process, with of course the let's say unsustainable also findings associated with it, are put in the background, investing instead in the 3D visualization reliability that returns an object that is even more surprising than the reality itself. This leads in the process also to the entry of new creative profession into the digital production chains. For example, here we have Ada Sokol, that is a 3D artist, really popular. She collaborates with major fashion brands and create a realistic 3D object that have a sort of digital behavior. For example, here those glasses melt over time. So it is important also to consider which kind of professional figures a brand wants to integrate inside their team to provide this new experience to create a digital products. Of course, as anticipated, the blockchain technologies make it possible to certify the product together also with the production process of the whole jewel, an area that is still difficult to achieve concretely in jewelry, but which gives the brand the opportunity to build the customer loyalty while respecting the planet and of course people. This is an example of Manuganda that introduced the digital passport of the jewel. It is a digital twin of the physical object, which can transfer digitally all the features of the jewel itself, but also the production, care, and maintenance features and indication. Then perhaps one of the most innovative and discussed also areas in this period about process dematerialization is the entry of artificial intelligence as co-creator of the product itself. We have Midjourney, we have DALL-E, we have now ChatGPT for text. We are now seeing the effective application of AI in the creative process. There is much discussion about the role of AI and the designer in comparison, but I wanted to focus on the collaborative aspects that the two terms can present. In this example, the AI was asked to make earrings similar to Mondrian paintings. As you can see, the relevance to the reference is really precise and perhaps is also quite literal. Or again, the use of generative adversarial networks offer formal inspiration that the designer can rework or use as a final object. In a process of co-creation, the designer's role, of course, is changing, but does not die. The machine becomes an intelligent tool for expanding the creative boundaries of the designer minds. who then has, of course, the role of applying his knowledge to create effectively the final object. Finally, services are dematerialized. As we have seen, of course, retail is the most influenced by digital experience. From try before you buy application, virtual try-on application that allow you to view the object from home, up to virtual exhibition, such as the one promoted by Sotheby's Auction House. So also a traditional auction house is applying these new innovative virtual technologies. Digital is able to immerse the customer in a new intangible context. For example, marketplaces that are digitally influenced, like jewels, marketplace for digital jewels that sell digital jewels, or House of Web3, that is probably the first retail platform which is fractionally owned and operated by its own community. And it is precisely the concept of community that becomes essential when we enter virtual contexts such as Decentraland or Roblox. These are the, here we have the brands that moves to reach the young customer, all of it that is already present on those platforms, and start providing unique shopping experience, events, or as we saw last year, the Fashion Week. But the experience can also pass through platform or website that are becoming more and more interactive. I have included here 3 examples, the Gucci Garden, the Vogue Talent, and the Mondo Genius by Moncler website, because I think they are good examples in terms of interactive platform that shows how the static images is no longer enough to communicate with the viewer. So the degree of immersion, virtual or otherwise, that brands can achieve become now essential to improve the communication. Last, but of course not the least, gamification. Between in-game advertising or advert gaming, brands have been able to reinvent themselves and create games and collaboration to involve Gen Z, especially, in an increasingly gaming platform. Louis Vuitton, for example, celebrated the anniversary of the founder's birth through Louis the Game, where you can play as Viviane, that is the company's iconic symbol, flower, that takes you to discover the brand heritage while you are collecting unique digital artifacts during your journey. The example I have brought you want to reflect on the very first word that characterized the name of my speech, phygital. Luxury and its physical features will never fully compensate for the digital transformation, so will never die. I want to use the expression, the word of Tomás Maldonado, that is an Argentine artist, designer, and philosopher, that has always believed that the body and its physicality are essential for us. And it is in fact undeniable that in the experience of jewelry and luxury, the physical component will always remain present. But of course, will be enhanced by the digital one, that is pairing traditional values such as exclusivity, craftsmanship, or authenticity in an intangible context. A phygital experience like the one, for example, promoted by Tiffany at the Vision and Virtuosity exhibition in London, where the Tiffany diamonds were exhibited and only the participants in the exhibition could wear it digitally, of course, through augmented reality. So we have the exclusivity because it is only for the exhibition, but then we have the possibility to wear a diamond digitally that we can't really try in a physical realm. Or, for example, Gary James McQueen, who, in collaboration with Jewels, the marketplace that I was talking before, creates this digital crown for Queen Elizabeth Jubilee. That is a way to offer the public the opportunity to participate in an event, feeling part of the celebration. Now I think I have run out of time, and I would like you to leave you with this question. What's next? Because of course, if the pandemic has definitely opened the doors to digital, now it is time to formalize progress and set the processes, understanding how to use digital beyond trends, and but instead with a sort of view to sustainability and creative growth and of course innovation. Thank you.
Yeah. Thank you very much, Beatrice. You stayed perfectly in time. And yep, thank you also for this very lively presentation. I can assure you that just like Daniela's remotely presented paper before, your papers are very well understood and received here in the meeting room and by the audience. And I'm sure the same will be true for the next presentation by Frank Cooper. Frank cannot be here. His nickname is Big Frank, so if he would be standing next to me now, you would perfectly understand this nickname. So Frank has recently, unfortunately, retired from his role as a senior lecturer at the Birmingham City University School of Jewelry, where he was also responsible for the Center for Digital Design and Manufacturing. Despite his retirement, Frank has continued his work with companies in the UK jewelry industry as an independent consultant. Frank is an award-winning and well-known speaker here at the JTF, as well as the globally renowned Santa Fe Symposium on Jewelry Manufacturing Technology, where he was willingly sharing his knowledge and insights into the development and use of various 3D printing technologies and additive manufacturing, particularly the additive manufacturing of precious metals. So in his overview paper on additive manufacturing and applications, he will cover the development and use of 3D printing in the jewelry industry. He will also discuss in some detail the current state of the art and finally take an in-depth look at the future. A future where we can expect to see innovative new technologies on the horizon that could transform some aspects of jewelry design and manufacture from the more traditional use of 3D printing into the world of additive manufacturing in the global jewelry industry. So Frank, please start.
Thank you, Jörg. Okay, so we're going to consider the DNA of 3D printing. Next. Next. So, like I say, we're going to consider the DNA of printing. So how 3D printing. Next, yeah. The development of 3D printing. Oh, no. We're going to have to stop. This ain't going to work.
So should we swap presentations? Maybe continue with the next, then give you the time maybe to restart.
Yes, please, yeah.
Yes, start the presentation in half an hour or so.
Mm-hmm.
Yeah. So yes, if this is a suggestion, sorry, Frank, we will support you with someone calling you, and then I guess it will work out later. Don't worry. Yeah, we definitely want to hear your presentation later. So let's continue then with a shared presentation from Alejandra de la Hia. I don't know if I pronounce your name correctly, and Andrea Friso later on, both talking about binder jet technology, with the first presentation on functioning and working. So Alejandra currently works in the HP Hewlett-Packard 3D print team in Barcelona as an application engineer for the new HP Metaljet S100 solution. She joined HP's team 5 years ago as procurement engineer and vendor manager. Prior to HP, she worked for various companies in the automotive industry, both in Germany and United Kingdom, developing projects and products as mechanical engineer. She holds a Master of Science in Mechanical Engineering by the Universidad Politécnica de Madrid, and also is part of the mentorship program Inspira STEAM in Spain to inspire young students to follow technical careers. In her presentation, she is talking about Metaljet technology that represents a new approach to metal powder additive manufacturing of metal parts, well established and proven across several industrial sectors for production of stainless steel-based applications. Metaljet is currently being introduced also to the world of jewelry, and this is why you're here, and fashion industry to unlock and open up new opportunities and manufacturing options. This presentation will deal with the concepts behind binder jetting, the enabling processes, and unique applications of a Metaljet printer. So, we look forward.
Hello, good morning, everybody. So yeah, as my colleague was saying, my name is Alejandra de la Hija. That's the way to pronounce it, so you are not that far away. I work as an application engineer for Hewlett-Packard for HP, specifically for 3D metals printing. To give a little bit of background, yeah, I'm short. To give a little bit of background, in HP, we have the headquarters for additive manufacturing in Spain, in Barcelona, although we split the development between the US team and the Spain team, but the core of the technology is basically developed in Spain. I work as application engineer, so my job is to work very closely with customers that want to use our technology and help them in the design process, in the development process, until the parts are ready and stable in mass production. Before we go too deep and technical into the technology, I want to explain a bit the journey that we have been going through since we started to develop the technology. So binder jet technology was born many, many years ago in the MIT. It's a technology that we have been studying for many years already at HP as an incubation technology. But it was in 2018 when we finally announced that HP was going to invest in this technology because we saw a lot of potential to be able for the first time to manufacture 3D printed metal parts at scale with quality, productivity, and cost efficiency. So in 2018, we finally announced that we were going to develop this technology, and how we developed this technology was by strong partnerships with key players from the industry. So in 2020, we already started conversations with Legor to understand how we could impact in the jewelry industry as well. And we've been testing with Legor for a couple of years, parts, products, materials, so far and so on. And finally, in March 2022, we proceed to the installation of the first units in Legor. And also, an important milestone for us is that in September this year, we finally announced publicly that our final solution is commercially available for every customer that wants to invest in this technology. How we are working with customers, it's a double approach. So we want to be very close to the OEMs, which basically are the companies that have designs that can be produced with our technology. These can be companies from every single industry. And these companies, some of them will want to have a vertically integrated manufacturing, meaning that they will be producing their parts in-house with their own printers. But many of them will just want to buy the parts from strategic partners. So that's why we keep on growing our network of partnerships with contract manufacturers or with experts of powder development like Legor. So we like to be in the middle because we've been in contact with customers from all the industries for many years, and we understand well how to communicate with customers and how to be able to transfer projects to contract manufacturers.
Right, done that.
He seems to be ready. So here I present you
Yep.
our solution. We don't like it. We don't like calling it only a printing solution. It's an end-to-end solution for the mass production of metallic parts. You see in the middle the printer itself, but on the sides you see also the powder handling solutions, which we believe it's very important to have in order to automatize as much as possible all the process of the powder handling. So the focus of the development of the technology has been from day one productivity, cost efficiency, and quality to really be able to produce at mass production volumes metallic parts. Before I explain in detail BinderJet, I wanted to give you a little bit an overview of what are the current additive manufacturing technologies. We have here a graph that's evolving every year. I was this year at Formnext. I was surprised to see all the many new technologies that are coming in the additive world. But I think when looking at specifically metals, which is the sign that you can see in the bottom, like with a magnet sign, there are three key players. You have directed energy deposition, which probably was the oldest 3D printing technology developed for metals. Basically, it's a robotic arm that deploys metal powder fused with a filament and with a laser or an electron beam. It's quite old. It's mostly used for very big parts. The quality, it's a little bit questionable on this technology. Then probably you are all quite familiar with powder bed technologies, most commonly known as laser technologies, which are probably the most stable technology right now in the market because it's been for many years in the market. The bottleneck for laser printing is productivity and cost efficiency. So for prototypes, normally it works well. It keeps on increasing the productivity, but scaling products at mass production with cost efficiency, it's a little bit of the bottleneck of the technology. So that's why BinderJet was born. You see it in the middle. This is where HP has developed their own solution. It really helps to create, to have very good productivity and to tackle mass production volumes. Not working anymore. The next slide, it's a bit heavy in size, so maybe that's why it's taking some time. Okay, here we go. So what is the process itself? Here we say HP Metallurgy, but it's quite generic to BinderJet in general. So we start by spreading a layer of very thin metal powder over the build platform in the printer. And then we come with print heads, very common, very similar to the ones that you will have in your printers at home, that put ink exactly where you want to print the part. We do this it's a surface-based process, so basically with one pass of the print heads, you are printing the full area that you want to be printing. The ink that we deposit in this technology, we call it a binder. Binder, which is basically a glue that glues the metal particles together. So we keep on doing this layer by layer. Basically, you will come, you will spread another layer of powder, you will put again the ink using our print heads, and you need to do this by applying a certain level of energy. Why you need to apply a little bit of energy is because our ink is a water-based ink, and you need to start evaporating part of the solvents from this ink. Also, it's important to apply energy because you don't want the ink to go into further layers. You want the ink to fix in the layer where you are exactly printing in each exact moment. So basically, once you finish the printing process, you do layer by layer with the print heads, putting the ink. You need to apply even more energy because this ink is basically a polymer, and you need to cure the polymer to make sure that the chain of the polymer is really activated and you are activating the glue mechanism of the polymer chain. So you apply this energy, which we call the curing process, and finally what you have is basically a box that's filled with powder that has not been printed and parts that have been printed. We call these parts green parts. It will be similar to the brown parts in powder metallurgy. which are still not fully dense, which are still not fully sintered, because basically the metal particles are only glued together. So once you do the excavation process, this means you take out the parts that have been printed and you retake the powder that has not been printed, so you can reuse it in the next cycle. You apply finally a sintering conventional cycle to the part, and you obtain the final solid part. To this part, in the last image, what you can see is you can do any post-processing that you will do to any other metallic part. You can post-machine the part if needed. You can heat-treat the part even more if you need to. You can polish the part. Any other thing that you will do to any other conventional metallic part, you can do to binder jet parts. So what's the advantage of additive manufacturing in general over conventional metal? It's, I think, the most important key benefit is freedom of design. So it helps to generate very innovative products that with conventional technologies, it will be quite hard to produce. Also, it's important to think about how fast you can iterate many different options, because you can print many different designs at once, and you can qualify them, you can validate them in parallel as well. And most importantly, it's a tool-free process, so you don't have the pains that you will have in product development with conventional technologies, because you don't need to invest in expensive tools. What is binder jet bringing to the additive manufacturing industry in general? It's the productivity and also the raw materials. So basically, productivity is clear because, as I was mentioning, it's an area-based process, so you are printing the full area with one pass of the recoater of the printhead, compared to laser, where you have to be printing point by point each single particle. Also, another advantage is that since you are sintering the full mass of the part in the furnace together, you get very isotropic properties compared to laser printing. And finally, since you are printing only green parts in the printer, you can stack parts vertically in the printer without the need of printing supports, which means that you reduce also the processing steps that you will require with conventional laser printing. Important to highlight as well is the metal powders. We are leveraging the ways of producing the metal powders that are used in metal injection molding. This helps to really reduce the raw material cost significantly as well, which in the end drives the part cost as well. And what is metal jet, HP's metal jet advantage over binder jet ecosystem in general? The way I like seeing binder jet, it is the most similar 3D printing process to paper printing, because instead of printing with your printheads in paper, basically you are printing with your printheads in a powder base. So we have been, at HP, we have been printing in paper for more than 40 years, and all that knowledge that we have in-house has been put in the development of our exclusive binder jet technology. We are leveraging our knowledge on printheads, and we are leveraging our knowledge on inks to create this binder that we have in the market today. How the process works itself. In the previous slide, I was commenting how the printing process works and how the current printing process works, which are the two middle pictures you have here. But this is not the only solution that we have developed. As I was mentioning, if we want to drive part quality, if we want to drive productivity, it's important as well to automatize as much as possible the powder handling process. So how we start, basically we start either with fresh metal powder or with recycled metal powder. We can use both, we can use a combination of both as well. And you will load your build unit. The build unit is the small unit that you see in between the different stations, which is where the metal powder is traveling and where the printed parts are traveling. So basically, we have first our powder management station, which helps to mix and sieve and have very homogeneous powder distribution in the full powder that you are loading. And you will load automatically this build unit that will be ready to be printed. You will take, it's a card with wheels. You will take this card, you will insert it in the printer, and you will start with your printing process. When you are done with the printing process, you will need to move to the curing station. We do the curing station separately away from the printer because we want the printer to be doing 24/7 what it does best, which is printing. So we consider curing is not what the printer does best. So that's why we do the curing in a separate curing station. Once you have the parts cured, which means the binder is activated, the metal particles are glued together, you will need to do the depowdering. Of course, you can do the powdering manually with vacuum system, with an operator, but this will take long time. So for low volumes, this makes sense, but when you are thinking about high productivity, it makes sense to use our automatic depowdering station, which with our combination of airflow and vibration helps to depowder the parts, so they are ready to be taken and to put in the sintering furnace for the final sintering process. As I was saying, all the powder that's collected from the depowdering station can be put in our portable tanks and be reused in the next cycle, because basically the metal powder in the printer, it's only heated up to 70 degrees, so there is no damage being done to that powder, so it can really be recycled without issues. Now, why we chose this technology in particular? So when we look at the portfolio of technologies that exist in the market and the market size, it's an 800 billion market size in mass production of metal parts. $800 billion with technologies that have not been really disruptive for decades. So we have metal injection molding, investment casting, press and sinter, machining, forging, stamping, joining, and welding. The newest technology was metal injection molding that was put in place in the 70s. And since then, no new technology has come in the market to really try to disrupt the production of metallic parts. So that's why we saw a niche there to be able to create parts with innovative designs, design freedom that could disrupt the production of metallic parts. Each single current technology has its own pain points. So when you are thinking about producing a part with binder jet, it's important to understand which pain point you are trying to overcome from these technologies. Because if you are just trying to substitute a machine part with a binder jet part with the same design, most likely you will not be successful. Machining is very stable technology. So if you are looking into machining, for instance, a very complex geometry, you have a lot of material waste, it doesn't really make sense to machine that part, maybe that part is a good fit for binder jet. So it's important to look at which pain point you are killing from each single technology. So the product can be successful in binder jet. It can be that you need to iterate faster. It can be that you don't want to invest in tooling because you have maybe low volumes in production and you don't want to make that huge investment in tooling. So the key benefits, the way I see it, for binder jet in general, are the ones that you see here in the bottom, which basically is to enable new geometries, to have design freedom. Also, it's important to look at part consolidation. Many times you have many hours of assembly time with conventional technologies that maybe you don't need to have with our technology, because you can print several parts at once and print several functionalities at once as well. When looking into jewelry, customization is for free, so you can customize every single product for free because you can print all of those parts together in a digital way. So customization in the jewelry industry could be quite interesting as well. We are enabling new sizes, especially we compare with MIM. The largest MIM part in the world weighs around 400 grams. We can produce parts that weigh up to 1 kilo. So in some cases, we are actually enabling also new sizes. When looking at surface quality, it's also important to highlight that binder jet in the portfolio of additive manufacturing techniques is the technique that enables better surface quality. And specifically with our solution, what we are told by customers is that we are able to achieve very good surface roughness compared to other technologies as well. And finally, the turnaround time. So as I was saying, you can qualify, you can develop many products at once because you can print them together. We have a customer that's very happy about using our technology because previously it was taking them up to 2 years to go to market with a new product, and with our technology it's taking them only 6 months to develop a new product. So this is something interesting to look into as well with additive. Now, which parts are a good fit for the technology? I think it's important, this is not rocket science, but I think it's important to understand really that this is a technology that has been developed for mass production of parts. So if you are looking only to create a prototype of one single part and then move to a different technology, binder jet is not going to be the right fit for that part. So it's important to think about components that will be serialized with the technology to take the full advantage of the productivity that the technology can offer. Then looking at size and shape, it's important to look maximum recommended size that we give is a tennis ball size or a fist size of a part, because like this you can put many parts in a printer and take the full advantage of the productivity. We can print, of course, bigger parts than that, but maybe from a cost point of view, it will not be so efficient. Then from a weight point of view, as I was saying, we can produce parts of up to 1 kilo. Over 1 kilo, the sintering becomes a little bit challenging. So when looking at products that weigh even more than 1 kilo, we can look into topological optimization, look into ways to reduce the weight to put the product into the spec, let's say. Also, it's very important to look at how the product can be stacked in the printer. So if it stacks very nicely, you can put many different components in the printer, which will help to drive the economics down as well. I was talking as well about product complexity, and many customers tell us, but how do you measure a complexity of a product? It's not easy to measure the complexity, but a way to see it is imagine that design, imagine how you will CNC machine that part, and if you require more than 4 and 6 tool changers or setups in the CNC center, that's a design that's complex enough to consider binder jet technology for that one. And then finally, a little bit of design recommendations. The main bottleneck from a design point of view is the sintering process. During the sintering, you are really heating the material to a point that's very close to the melting point, so you have effect of the gravity acting over that design. So it's very important to think about how that design is going to be supported during the sintering process, and we can help on that thinking as well. From a design point of view, you were seeing it in the previous slide, more than half of the industry in metal production is produced with machining. So designers for metal parts are very used to think about machining, which basically you start from a block and then you start removing material. With additive, it's the other way around. You start creating material from layer by layer, basically. So you will need to think about what are the interfaces and add material only wherever you need it, not think the other way around about creating a block and remove material by a CNC machine, let's say. When talking about the wall thicknesses, the minimum recommended wall thickness is around 1 millimeter. We can go lower than that in specific cases, but the minimum recommended is around 1 millimeter, and it's important to have uniform wall thickness as well, transitions. This coming from the sintering as well, otherwise you will see distortions that are not wished. And finally, looking at small features, pins, holes, cavities, so far and so on, also the recommended size is around 1 millimeter.
Yeah, thank you very much for this very good introduction into the binder jet technology. We go into the second part of this presentation held by Andrea Friso. He is the R&D manager at Legor Group for Master Alloy Business and has a strong experience in precious metals metallurgy and its relationship with jewelry production processes. He coordinates the conception, testing and release to market of new Legor alloys and constantly supports technical sales teams in Legor worldwide. In his presentation, he continues talking about binder jetting and the comparisons with existing jewelry processes. The presentation is focused on introducing the binder jet technology in its applications for jewelry making and showing results from 10 months of use of this technology at Legor laboratories in Bressanvido, Italy. Practical experiences of testing and production using binder jet will be shared during the presentation in comparison with other and still better known technologies. Thank you.
Buongiorno a tutti, noi ritorniamo in italiano.
Good morning, ladies and gentlemen. I'm now going to follow suit to what Alejandra de la Grija had just said to us. We're going to get further into detail when it comes to gold jewelry and the fashion industries to see how this technology can be best used for these industries. So today's objectives have again to do with the binder jet technology in its applications in the world of fashion and gold jewelry. To this end, we are going to present a comparisons between the different technologies being used in the industry, and then we're going to see the results as obtained in our experiments, the experiments that we carried out as our labs. First of all, why has Legor opted for the binder jet technology? Well, because it combines the best of some of the additive technologies already in use when it comes to the manufacturing of minute parts and jewels, such as SLM and MIM. I greatly appreciate the description by which binder jet could be a digital MIM, whereby basically we can shift from a CAD design to the finished product in no time, as is typical with SLM, with a high productivity rate and good quality standards, as we find with MIM, metal injection molding. Binder jet grants a number of advantages in that the surface roughness is lower than that which go with other additive manufacturing technologies. There's no need for supports that use up additional material, which is again another very interesting finding when it comes to precious metals indeed. And then this technology is one which uses up very little powders, because the powders basically can be reused at the end of the cycle. So these features, combined with a number of assessments that we made on the results of the experiments that we carried out, persuaded us onto carrying out further experiments with this equipment and to buy 2 prototype units that are equipped with all what is needed to manufacture finished products. Between March and September, we've optimized, we've used basically the material, which is a steel, and we've used this steel basically to get better trained in using this piece of equipment. The final objective was to use materials that are better familiar to us. Obviously, jewelry is our core business. So as from November, we've been using bronze, silver powders with the sintering processes and printing processes to better use this equipment. As for the technologies that we wanted to compare binder jet to, because we believe that there are technologies can be replaced by binder jet. But the first that I can think is microcasting. Microcasting is perhaps the process which is best known when it comes to jewelry and gold jewelry making, which is off the shelf. Again, of course, it can be used for any type of metal used in jewelry, and it grants also a very good roughness of the object that's cast. And this is something that we want to consider, because this requires also a better reduction in size, in that we're going to use also less material in the polishing stage, in the finishing stages. We know that microcasting has one major issue, in that it is very much an empirical process. It is very much operator dependent. It very much depends on the skills of the operator in stabilizing also certain processes, certain dynamics. And you have to carry out a very accurate process also in looking at the defects when it comes again to microcasting. And the environmental impact is certainly most relevant, because obviously the investment is to be, there are fumes that are generated because of the burning of resins. There is a silica to be dealt with, of course, when the investment is removed. Because of all these issues, again, the process is not very green, basically. SLM. Selective laser melting is the other technology that we've compared printing with. This is the technology that enabled the gold industry to shift from the design to the manufacturing. This is certainly very practical to the development of prototypes. A small series, basically, of products. It allows for a very limited reduction in size after the finishing of the piece. It is very suitable to have a unique piece, again, available immediately after having the design of it. When it comes to productivity, when it comes to precious jewels, selective laser melting requires a certain amount of material to be used, and obviously this had to be in line with the investment that we wanted to make. There's a certain speed we can produce at to grow and have a good quality of the product. So sometimes laser has to be used repeatedly on the same edge, on the same side of the object, so as to reduce roughness at best. And this, in a way, reduces productivity because it adds on time. There's an additional aspect that of reusing supports and powders, which obviously can add to the material being consumed. MIM, metal injection molding. Well, this is a process that we don't use for gold jewelry making. It uses plastic injection printing technology. We use metal powders that can be binded up together with a polymer that can be cured up, heated up, and then be made printable within a mold. This technology is marked by a very high level of productivity, and it is highly automated as a process. So it works very much for mass production because it requires little labor, low human resources basically to operate it, and it manufactures at very high speed. Yet there is a problem in that molds are to be developed, and those may be very costly. They could cost up to thousands or up to 50,000 euro for one mold just to have one single object. And it is a subject to important reduction in size. And that could be is an issue. There is also problems also in terms of the undercut, so you cannot have a complex items because again the undercuts are not admitted, so we don't use this technology for gold jewelry making because with gold jewelry we have non-standardized products. It is not a mass production. As for CNC devices, well, CNC works very well when it comes to using little tolerance object. This is why it is widely used when it comes to watchmaking. The watching industry requires assembling different parts to have a final element, as for example a bracelet. It can be used for different metals. As a matter of fact, usually CNC are used when all semi-finished products are already added. So with microcasting, you can have problem with so you don't have any problems with the materials. But if it can be difficult to use it at the there may be a lot of waste, and it could be because of the lathing stage, or sometimes that waste can be cast, but there are maybe other powders that actually cannot be reused. So again, the problem with CNC is that a lot of waste are generated. Not all of these can be reused. Another aspect I was hinting to earlier on and that is the management of a workshop. For when I use this CNC equipment, I have to understand what is the mindset again behind this. I have to have tools, I have to have specialized resources. So with BinderJet, as with this, you basically have to understand how it works. You have to understand what are the strengths and weaknesses accompanying the individual technologies. We've heard that there's very good flexibility with BinderJet, similar to SLM, and this is a great strength for the BinderJet technology. Another important strength is that there is a medium to high productivity, because on the bed you can have different objects with different tolerances, with different shapes, and then you can work with different layers. So you can work with different levels. Again, you can work with different items for the BinderJet. In the world of jewelry, this is a little known technology. Even the costs connected with this technology is very high. The investment is quite relevant. There are aspects to be considered, as for example, the risk of geometrical deformation when the sintering is entered into, or the reduction in the size that can be different at different sides of the objects. With reference to productivity, we have identified certain values as to rank the different equipment for the manufacture of one individual item. An item that could be of interest for the gold jewelry industry or the fashion industry. In this case, metal injection molding MIM ranks first, because with this object, you see that with 4 hours, you can obtain as many as 3,000 items. The cycle of 2 days, well, the first day can be used for the printing of object, and subsequently the sintering is to be performed that can take as much as 10 to 15 hours with the different steps from green to brown to sintering itself. With microcasting, you see that the productivity is halved vis-a-vis metal injection molding, and it requires many more working hours. In this case, indeed, as many as 2 people are required, one devoted to the waxing and one for the casting. And then mass production can be obtained for a number of trees. So in 2 days, basically, you can have as many as 3,000 items. This is the estimate that we arrived at for this microcasting. In the case of binder jetting, you can fill in the furnace, and in 2 days you can have as many as 2,000 items. So this would require, this is similar to one complete cycle of sintering. One cycle of sintering is to be carried out after the jetting. The powdering also has to be included. In the case of CNC, starting from a semi-finished product with 8 hours of work, only 100 pieces can be obtained, which is more than can be obtained with the selective laser melting. But certainly it is a completely different order of magnitude if compared to binder jetting. So binder jetting has a pretty high productivity, and that makes it very interesting for our processes. Another important aspect to be considered is the environmental impact. We've already said that microcasting has an important footprint on the environment because of the amounts of material which is wasted, as in 20% can be considered as connected to the bottoms of the sprues, and there are also investment to be disposed of, and this obviously bears importantly on the environmental footprint. With CNC, the footprint is lower, but yet there is a lot of waste which is generated. Also because of the oils that are used and that are to be disposed of after a certain number of cycles. Now, a greener technology could be the SLM, which has a low yield because I always have to fill up all the volume with powder to obtain all of the net, and I have 80% of the powder that I use, with 10% of supports being obtained, and there's low productivity accompanying SLM, so each item basically bears more on the environment. As for MIM and binder jet, well, the difference between these two are the following. MIM still requires some feed. There's 10% of the material that is wasted because it is removed to come up with a finished product. The powder that can be reused when it comes to binder jet printing is as high as 85%, because I have a slightly higher yield. I can work at different levels, as we said, and the powder may be reused later on, as we've just seen. As for our experiment, we have chosen selection of objects. In the first months, we have printed with Lago, Mr. Lago, my colleague, we've printed a number of items of different and increasing complexity to come up with a number of evaluation on the quality-wise and quantity-wise, so as to come up again to some kind of a comparison with our survey, measuring the quality and quantity of in our products as comparing the different technologies available at our workshop. At the beginning, we only used one type of steel, AISI 313, then we used another type of steel, and then we're still carrying out further tests on using bronze and 925 silver. Qualitative tests have been performed on the sintered object. Then we looked at the digital microscopy. We measured rugosity on the different level of the, and we looked at the residual porosity on the items produced, because certainly this is an indicator of the surface quality. In the case of pores, for example, we might have problems leading to fractures or reduction of strength. In the case of jewelry, obviously, this is not pretty much the issue, but it can be an indicator, porosity again, can be an indicator of the degree of defects that we may have because of cavity, because of defects, because of dents. So a very low porosity in itself is an indicator of what we're going to have after the polishing, after the finishing of the products. Now, we're not going to analyze every detail of this chart, just look at the first lines. An acceptable quality when it comes to fashion and gold jewelry industry, well, roughness on a polished product should be lower than 1 micron, so 0.6, 0.7 would be acceptable. But looking at the item as a sintered or as cast, so before the finishing, basically steps, on an average of items that have been assessed, we've identified MIM as the technology which is accompanied with a lower superficial roughness, which possibly depends on the pressure which is used in the mold, compacting the item. There could be higher in the porosity yet, and then we with microcasting had similar granted a similar roughness, superficial roughness. It was not accompanied by other defects. In the case of steel microcasting, was pretty much of a challenge. Indeed, the porosity of the products would not be acceptable when it comes if those items were thought of for the gold jewelry. We also had a very low porosity with SLM, with the surface roughness of 4 micron, which doesn't compare with the one of microcasting, but still it is much lower than the one we saw with SLM, where the roughness was higher than 10 microns. The reduction in size is also to be considered. With MIM, we have a reduction in volume of some 20%. In the case of the binder jet, we saw that this reduction in size depends on when the binder was added to grant the adhesion among the different layers of powder, and this is something that should be considered again when the item is, when this jewel is designed. We solved many problems repeating the test and sometimes redesigning the item with adequate software and CAD equipment, or with ad hoc supports that would guarantee the correct sintering. As for bronze, this is still a work in process. The roughness we obtained was somewhat less than 5 microns in the case of the product as obtained with binder jet, which is interesting but not low enough. The internal porosity is still too high, certainly through the sintering cycles, and this has to be reduced. In the case of bronze, microcasting was the technology that granted the best results with the roughness of the item as cast of 1 micron, which is certainly very attractive, and internal porosity that was extremely low, indicating that this type of material, such as bronze, is really perfect for the world of jewelry, because the best results were obtained again with bronze. Well, this is a bit too early to come to conclusions. It is a bit too early to say whether binder jet is readily available for the world of gold jewelry, because, well, the material is still lacking. There are specific alloys to be developed for additive manufacturing with binder jet printers. There are issues that are to be managed also when it comes to the management of so many powders, so we have to work hard over the next few months to develop adequate materials so as to see whether, again, they can be best used with this technology, binder jet. Productivity is certainly very high, and we've also seen a good surface quality. Grain fineness appears to be compatible with binder jet. We can hopefully meet soon to see whether this technology can be used with bronze and silver, because tests are going to be performed, and then we're going to try and test also gold and platinum. These are the objectives that we set on ourselves for the future, so as to carry out a comparison again with the same technologies using the same material. Certainly this technology probably is going to be added and not to replace other technologies, but this is something that we're going to see in the near future, hopefully. Having said as much, I'd like to acknowledge my colleagues, and thank you very much for your kind attention.
Thank you so much, Andrea. I think we will all be hearing and discussing about this technology in the next months and years. So, the plan is to come back to the presentation of Frank Cooper. Frank, I can see you. So let's restart with your presentation and the overview on additive manufacturing technologies.
Okay, thank you, Jörg. Right, my apologies for the technological cock-up earlier, but let's hope this works this time. So we're going to have a look at the DNA of 3D printing, which eventually led us to the world of additive manufacturing. Printing led us to 3D printing via technology, which eventually led us to additive manufacturing. We're going to have a quick look at the past, a quick look at the present, and a slightly longer look at the future. In the beginning, there was block printing, wood block printing, developed in Japan about 2,000 years ago. As things move on, as technology moved on, we had things like the Gutenberg press, the mechanical typewriter, lithographic printing, and mechanical lithographic printing, and of course the Xerox photocopier. Technology continued to move on, particularly with computing power, which gave us word processors, desktop computers, laptop computers, tablets, and of course our very favourite smartphones. 3D printing was thought to have developed from topographical modelling and something called photo sculpture, both well worth researching if you have the time and the inclination. Modern 3D printing was developed by this guy, and first Charles Hull, and first patented in 1987. His process was known as selective laser sintering, SLS. This led us to selective laser melting, or SLM. And this, of course, eventually led to additive manufacturing. Additive manufacturing, or metal printing, has a number of different names. Direct metal laser melting, direct metal laser sintering, selective laser melting, electron beam melting. Well, there's a general catch-all term used, which is powder bed fusion. I was at this point going to cover binder jetting, but clearly Alejandra and Andrea have made a far, far better job of it than I ever could have. So let's check out the road to additive manufacturing by the jewellery industry. And this is a personal journey down my road to additive manufacturing via the School of Jewellery in Birmingham. It all started a long time ago with the Sanders Model Maker 2, a very temperamental Sanders Model Maker 2. We eventually invested in a number of different solid-scape machines, which is the current version of the Sanders Model Maker 2. And these machines do produce excellent quality, repeatable and castable items. We also had EnvisionTech per factory. Again, inclined to be a bit temperamental, but over the years, EnvisionTech have developed a faster process. And again, they produce usable materials, very good for casting, and across a range of different resins. The Formlab systems are gaining a lot of traction in the UK, both for cost and ease of use. It also comes with a very nice and effective wash station and a reasonably sized build area, and it builds from the bottom up. Now, hopefully this video will give us an example of how this technology has moved on. This information was only released early in 2023.
First, we brought you a 3D printer that enabled you to make anything. Now, we're pushing the boundaries of what you can do with our 3D printers by bringing you the tools you need to make scale. Introducing Formlab's automation ecosystem, hardware, software, and material streamlining tools that transform your 3D printers into autonomous fleets for 24/7 printing made easy. Together, Form Auto, Fleet Control, and our high-volume resin system maximize throughput while minimizing labor and costs, so you can scale with demand more seamlessly than ever before. Instantly automate production with Form Auto, an extension of your 3D printer that enables non-stop throughput without interaction, reducing cost per part with labor savings of up to 80%. Enabled by our patented quick-release technology, Form Auto seamlessly removes parts from Build Platform 2 and starts the next print, so production doesn't have to stop when you leave work. Scale and align your business with Fleet Control. Advanced new features within Formlab's dashboard management software that equip your team with the agility to use shared printer groups from anywhere. Leverage a centralized queue that automatically sends your prints to the right printers at the right time, boosting productivity across your entire organization. Cut down on labor and waste with our high-volume resin system. At 5 times the capacity of a standard cartridge, you can print with 80% fewer interactions, 96% less packaging, and a lot more productivity. Whether you're using to scale production. First, we brought you.
Well, I hope you'll agree that showed in some detail how these technologies move on very quickly. Another piece of equipment we had great fun with at the School of Jewellery was the 3D Systems project, which eventually morphed into the 2500W version, which we absolutely loved to use, principally because it had, again, excellent materials with great castability, but also a rather large build plate, which made it appealing to the larger jewellery manufacturer. We also had a DWS X-Fab, a green laser machine, a great workhorse in the school, which again produced items in a resin that was castable and easily used. So we've gained all this experience in 3D printing, and over the years then, the idea of additive manufacturing began to gain traction in the non-jewellery industry, and we decided to investigate and perhaps invest in the technology. So the additive manufacturing of precious metals. Let's start off with what is additive manufacturing. Additive manufacturing is the process of creating an object by building it one layer at a time. It is the opposite of subtractive manufacturing, in which an object is created by cutting away at a solid block of material until the final product is complete. Technically, additive manufacturing can refer to any process where a product is created by building something up, such as molding, but it is typically used to refer to 3D printing items. I'm going to report now on some research carried out by an ex-student of the school, Maria Paparosi-Shipman, who now works for the Diamond Centre Wales on a Welsh government-funded project to explore the different technologies and options for the additive manufacturing of precious metals. So the research criteria she's used, number 1, ease of use. Number 2, material security. Number 3, the surface quality. And number 4, the economic viability, largely based around the build plate size and how much material is required to fill the chamber. So the technologies that were analysed were EOS, exact metal, desktop metal, hollow, and alpha laser. So this is me back in 2016 taking delivery of our Cooks and Gold EOS MO80. It should be said here as well that Maria also worked for Cooks and Gold at that time, and she was the senior technician in their additive manufacturing section. So she has a great understanding of this technology and its potential. These are some early experiments into using the machine where we were trying to push it to the limit. But the key thing here to remember is that additive manufacturing is not a replacement for casting. It is a new and it is an alternative method of producing precious gold items, of producing jewellery. Here we can see some early experimental work by the students at the school. An early lesson learnt by both ourselves and the students was the use of support structures. Using an SLM process, support structures are integral into what is produced, but they can be removed and post-processed to produce good, usable products, as you can see here with this watch bezel. What sort of products could you turn this technology towards? Well, clearly intricate and detailed items that are difficult, if not impossible, to cast and finish. This was one of our favourite experimental areas. Hollow items. We described them as jewellery items that had volume with very little mass. And of course, one of the key things you can do with it is flexibility and articulation. You can build chain mail, moving parts straight off the machine with no secondary sub-assembly. Here you can see an example of a flexible bracelet in 2 materials, biomaterials, so white gold on one side, yellow gold on the other side, and produced by Cooks and Gold on one of their EOS machines. A great example of how you can build articulated items directly off the machine. This is a close-up of the surface of that bracelet before polishing, and it gives you a good indication of the clever design. The clever design process that was used to give it that flexibility and articulation. Here's another example of a chainmail type build, specifically for an Austrian company called Boltenstern. Once taken off the machine and processed, you can see we have a fully movable and articulated bracelet and necklace. Another thing you can do with this technology is to stop the build halfway through and insert pearls, crystals, precious gems into the build, and then restart the build and build into it articulation. So here we have a short video of showing the inserted items being taken off the machine. This is interesting. This has just come to my notice again in early 2023. Bentley Motors have a very exclusive range of cars that they're selling, into which they've introduced solid gold parts. So you can see here the start-stop button, and clearly marked there on the left-hand side is the UK hallmark. Now you might think and look at this and say, well, actually you could cast that quite easily, which is absolutely true. Although it's not stated in the press releases that I've seen so far, it's my estimation that this is probably hollow. Again, another example of volume without mass. So let's have a look at some of the machines that Maria investigated. There was the exact metal group of machines, and clearly the XM200C, which is about the size of a filing cabinet, met all the criteria. It's neat, tidy, quite easy to access and use, and the build plate is about the right size and scale for the small to medium jewellery manufacturer. The desktop metal system was closely checked, but this is a true sintering process which requires debinding and post-processing in a furnace. An added difficulty with this technology is the fact that the material is held in a stick, in a crayon, in a binder. So getting that filled with precious metals would have caused quite some problems. And one that was very encouraging is a company in America called Hollow Pure Form. But they're not a machine supplier. They are a supplier of they're a supplier of a build service, a print service. And here you can see there, because it is a sintering service, they're huge desintering equipment. They offer great accuracy and very fine tolerances with a really good surface finish. They do it by a form of lithographic printing, but the key to this is their proprietary metal polymer slurry, which then produces a green state item. Once it's in the brown state, it is a fully dense part. On the right here, you can see the Diamond Centre Wales file that was used to test a build on the setting. And on the left here is the actual setting on the build. It's not red gold, which was the eventual aim, but it is in fact copper. Now the system that was finally arrived at and agreed on is this alpha laser system. Particularly because of this system for holding and containing the materials. Also, their debinding not debinding, depowdering system is very clean and neat. And also their software allows the Diamond Centre Wales team to actually set their own build parameters. Additionally, Alpha Laser already had parameters for platinum and silver, which they were happy to share as part of the process. Here we have another video that will show you the machine in all its glory. I hope you could see there the very clever cartridge system and why it does appeal. Early trials and tests on the technology, which has now been installed at Diamond Centre Wales, have proven very, very successful. They tell me that the results are comparable to castings and they're having no problem with surface finish. If you want to research this technology further, one thing I would highly recommend is you approach Damiano Zito and his team at ProGold and ProGold 3D. They are absolutely the best of the best in this technology, not only in making the technology work well, but also in what materials you can use. I highly recommend, if you have the opportunity to go over to T-Gold and meet with Damiano and his team, that you do, if this sort of technology interests you. Also, the guys at CISMA do some quite interesting stuff. Unfortunately, because of COVID and my retirement, I haven't had a chance to bring myself up to date with the latest developments at CISMA. And DWS, we'll go back to DWS because I was very impressed by their X-cluster chain building process. It just remains for me to say thank you.
Many thanks, Frank. Long applause here in the room. Speech has been very well received. Thank you again for this nice journey back to the roots of additive manufacturing up to the state of the art where we are now. We are approaching lunch break, but we are not yet there. We have some time for questions and answers. I have to admit, I have zero overview if questions have been passed over to speakers already. So let's find out. I also recognize or have been told that Sarah, our first presenter, has already had to leave. So I'm not sure if questions are there for Sarah and Daniela. Daniela, are you still there? Have questions been passed to you? So if this is not the case, then I think we proceed with possibly with questions to Beatrice, who was talking about digital jewelry. Again, here she was presenting remotely. I'm not sure if she's still there, and if questions have been passed to her. We have also micros, right? So if questions come up, we can also just stand up, take the micro, and yes? There's a question here to Beatrice. No, if this is not the case, then Frank is still there, I guess. So
I am, yeah.
Yes. So That's good to know. So if we have questions for Frank from the audience, spontaneously, so please come up here. You have a question to Beatrice. But Beatrice, are you still there online?
Yeah, I'm here. Can you hear me?
Yes, we can hear you, but you probably have to give the question from here.
Okay.
Because we recognized earlier that from the micro.
I think it works, yeah.
Do you understand him?
She's Italian, I think I can speak in... okay.
Yeah, okay, I'm Italiano.
Okay, I have a question. The question is, but the recent market crash of NFT and blockchain technology, and so the mistrust that the market, the population, the more broad population has on this new technology that is incredible technology. What do you think can bring to, what is the effect that can have on the value of this product that has in the brand and in the material value his strong point? And do you think that in the future this damage will be pass, or there will be always some consequences by this market crash? Thank you.
Thank you for the interesting question. I think you underline a point that is really important. So the effect of like digital transformation that could evolve also in time. So of course, NFTs has reached a really a lot of hype at the beginning, and then it is slowly decreasing in a way, as you perceived. I think that the important thing to reflect on is the adoption of this new technology and the fact of bringing new perspective in the world of jewelry, of fashion and luxury. So all in all, there are always being a sort of up and down in novelties and trends in terms of innovation and technological innovation. But the strength of brand is that they are able to interpret the signals of the contemporaneity, the spirit of the time, and insert their communication, their value inside that kind of technological innovation. So I think that it is something that changed the role of jewelry and fashion and luxury, of course, and but it is only a starting point. And if I answer your question or...
Yes, absolutely. Thank you very much.
Thank you.
Yeah, thank you, Beatrice. Are there further questions to Beatrice? If this is not the case, then questions on additive manufacturing and binder jetting. Do we have some of them here from the audience? Again, there are micros, so you can just stand up, raise your hand. Everyone is satisfied. All the presentations have been clear, so this is also good news. And probably lunch is already there. This would be the other good news. You are nodding. Thank you. So I'd like to take the opportunity to thank all the speakers, first of all, for their really good presentations this morning, and all the attendees to this morning session. Please enjoy lunch break and come back after lunch. I think we restart punctually at 2 o'clock. Yes, so see you later. Thank you.
So good afternoon. We are ready to start the afternoon session of JTF. So we will continue with the technical session, and then after the coffee break at 4 o'clock, we will have a session on sustainability and B corporations. So it's a pleasure to introduce the next speaker, Chris Corti, a highly respected lecturer on technical subjects of jewelry for Santa Fe Symposium and JTF. Chris Corti has more than 40 years of experience in the sector of precious metal goods, acquired Johnson Matthey and the World Gold Council before setting up his own consultancy company in 2009. He has a PhD in metallurgy at Surrey University, UK, and before working for precious metals, he worked in the energy industry in Great Britain and Switzerland. His presentation is called Jewelry Alloys in the 21st Century. So there is a strong perception that in our sector nothing has changed in alloy compositions used for jewelry application. But then if we go in depth, we see that it is not true. There has been significant change, and change continues to accelerate. And we will have a look at the changes in precious metal jewelry alloys, and we will also speak about manufacturing processes in current use. So Chris Corti, please come over to the podium.
Good afternoon. In our traditionally conservative industry, there is a perception that nothing much has changed in the alloy compositions we use for jewellery. But a little reflection shows that simply isn't true. There's been a significant change, and the pace of change is accelerating during this 21st century. The changes in precious metal jewellery alloys, gold, silver, platinum, that have occurred in recent times have been made to meet the needs of manufacturing processes in current use and to improve the performance of the jewellery in service. In this presentation, I will examine these developments in jewellery alloys, highlighting the advances that have been made and some deficiencies that still need to be addressed. It will be noted that some alloy technology developments, interesting as they are technically, have not led to successful commercial use, and possible reasons for this I will discuss. In talking about such alloy developments, they must be placed into context regarding changes in manufacturing processes, innovative jewellery design, as well as legislative constraints. The former includes the growing interest in powder-based technologies, and we've heard a little bit this morning on some of those technologies, and the use of CAD and CAM, while the latter, the legislative constraints, include precious metal content, the national standards that change from time to time, and alloying limitations that impact alloy design due to factors such as health and safety, and probably nickel and cadmium are two good examples of that. To conclude the presentation, this overview will look into the future. What further alloy developments can be anticipated against the background of changing regulations, social climate, and the introduction of new manufacturing technologies, as well as improved properties. Alloy developments in the 20th century and the present era. The understanding of the metallurgy of alloys and the effects of individual alloying metals on microstructure and properties, coupled with substantial improvements in refining technologies and assaying and analytical techniques, largely developed during the early to mid-20th century, a period when metallurgy emerged as a distinct science and technology, and techniques such as X-ray diffraction and optical and electron microscopy were also developed that allowed us to understand the microstructural changes that occurred during casting, deformation and heat treatment. This is a time when the evolution of alloys with tailored properties to suit manufacturing processes and improve performance began to emerge. Our knowledge over this time can be summed up in the publication of books such as Working in Precious Metals by Smith in 1933, the Edelmetall Taschenbuch, the Precious Metal Handbook, by de Gusser in 1967, and Gold Usage by Rapson and Grunewald in 1978. Apart from the major precious metal companies who developed a range of commercial jewellery alloys at this time, a lot of understanding of their metallurgy was also published by research organisations such as FEM in Germany. Many phase diagrams of the precious metal alloy systems were researched and published during this time. This is a time when this knowledge enabled the strengthening of certain alloys by age or precipitation hardening. Investment loss wax casting was rediscovered and developed for the dental and jewellery applications, and the use of grain refiners and deoxidizers became the norm. Smith's book was published at a time when such knowledge was only beginning to emerge. Smith gives many compositions of alloys that are familiar today, but for coloured carat golds, he notes the use of additions of zinc and cadmium to gold, silver, copper alloys, but there's no mention of grain refiners. White golds are also included as coming into commercial prominence as a cheaper substitute for platinum. And as well as the use of silver to widen gold, he noted two classes of white alloys had been developed, the palladium and nickel whites, utilising the strong bleaching power of palladium and nickel respectively, with additional alloying metals such as silver, copper and zinc added to improve properties. With regard to platinum alloys, he notes their use in jewellery at 99.5% content 995 fineness, with small additions of alloying metals to harden it, including iridium, rhodium, ruthenium, gold, silver and copper. He also reports that the platinum standard in the UK at 950 fineness, which is finding some general acceptance. The term platinum is also deemed to include some iridium in the alloy. He further notes that much of the platinum in use in jewellery is alloyed with copper to improve hardness and colour. For silver, he notes silver copper alloys of 925 fineness, standard silver, or as we know it, sterling silver, has been used for some 800 years for coins and silverware. He also reports on Britannia silver at 958 fineness as another UK standard, which is a softer softer silver copper alloy. The issues of fire stain and tarnish are discussed, and reports on work to develop tarnish resistant silver compositions in the UK, the USA and Europe in the early 20th century. He notes the better tarnish-resistant properties of silver zinc and silver cadmium alloys. Moving forward to 1978 and Rapson's book on gold alloys, we find more detailed information on alloy compositions of commercial carat golds, their physical and mechanical properties over a range of caratages. The use of grain refiners such as nickel, cobalt, iridium, ruthenium and rhenium in the coloured golds is noted. The use of small additions of zinc as a deoxidizer and its use in larger amounts along with cadmium as a substitute for silver in copper-rich alloys to reduce the redness of the colour in the coloured golds. The understanding of colour variation in the gold, silver, copper alloys is also documented, depicted graphically in the coloured triangle, which we've got here, and I'm sure all of you here are well familiar with that. Our understanding of the coloured carat golds and the influence of composition on microstructure and properties is perhaps illustrated by taking two examples. Firstly, when 18 and lower carat golds that contain copper are annealed after cold working, simply allowing them to air cool results in material that is hard and not as ductile as we might anticipate it for recrystallized material, and will tend to crack on further working. However, if the alloys are rapidly cooled in water, the alloys are soft and ductile and can be further cold worked. This is because quenching retains the high temperature solid solution phase. Slow cooling below about 400 degrees Celsius allows the precipitation of copper-rich phases and or the disorder to order transformation to intermetallic phases AuCu and AuCu3, which are face-centered tetragonal in structure, as we can see in the ternary phase diagram on the right of this slide. So here we can see the intermetallics that form, and we also have in these regions, two-phase regions, we've got copper-rich phases precipitating out. The problem does not occur in high carat 21 and 22 carat golds, which remain single phase right down to room temperature. The second example is how changes in composition by additions of zinc to gold, copper, silver alloys influences the workability or malleability. If we take the ternary phase diagram on the slide, it is represented by a prism with the three binary phase diagrams evident on each prism face. Again, we can see the regions of the significant region of two-phase structures in the phase diagram, and that's bounded by these curved lines at different temperatures. So quite a significant area at 18 carat and lower of two-phase microstructures. The amount of second phase in an alloy will influence how hard and how difficult to work an alloy is. The amount formed will depend on how close the alloy composition is to the boundary with the single phase region. Close to it, there will be a little amount of second phase precipitate. In the center, there will be lots. It will be a 50-50 mixture. MacDonald and Sister came up with a system of describing such alloys. Type 1 alloys are essentially single phase and are easy to work. Type 2 contains some second phase and are less easy to work, and type 3 have lots of second phase and are hard to work. 14 carat golds can be particularly difficult to work, so careful selection of alloy composition allows us to obtain golds that are easy to work, but then we restrict ourselves to the colour range that we can get. However, zinc alloy additions tend to contract the region of second phase in carat gold. So if we add some zinc to our alloy, for example, we can free up the alloy in terms of workability, as we can see in the table on the left. All three 14 gold alloy compositions on the table are the same yellow colour, but the zinc additions change the alloy from type 3 difficult to work, to type 2, easier to work, and even to type 1, quite easy to work. After this general review of the state of alloy development during the 20th century, it is appropriate to look at each jewellery metal in a little more detail. And we'll start with silver alloys. Apart from the standard sterling silver, 92.5 silver, 7.5% copper, special grades for enamelling, chain manufacture, casting and spinning have been developed. These contain additions of metals such as cadmium and zinc to improve ductility, and trace additions of silicon and boron for casting alloys. Zinc also improves melt fluidity in investment casting and acts as a deoxidizer in casting. For enamelling applications, it is necessary to limit selenium and tellurium impurity content. It should be noted that such impurities also cause embrittlement of your silver alloy. The two major drawbacks of sterling silver, and also silvers of other finesses, are its tendency to tarnish due to the formation of silver and copper sulfides on the surface, and the frequent occurrence of fire stain during manufacture of jewellery, which we can see in the ring on the bottom of the slide. Fire stain is an internal oxidation of the copper to form subsurface copper oxides, which show as a dark stain on the surface and are difficult to polish away. It forms on heating the metal in air, such as in annealing and in soldering. Consequently, a number of alloys that are resistant to fire stain and tarnishing have been developed in recent times. Probably the best known of these is an alloy known as argentium, which contains germanium as an alloying addition as well as copper. It typically contains about 1.1% germanium, and this forms an intermetallic phase Cu5Ge in the microstructure, and it enables the formation of a protective transparent germanium oxide layer on the metal surface to retard tarnishing and inhibit internal oxidation of the copper. Argentium also, interestingly, can also be age hardened. Many of the other new commercial alloys use germanium and or silicon additions or platinum group metal or gold additions to confer improved fire stain or tarnish resistance. Fischer-Bühner and his colleagues at Legor have recently reported the development of a copper-free sterling silver that is tarnish and fire stain resistant, where all of the copper has been replaced by base metals such as indium, tin and zinc, and some palladium. Sterling silver is a soft and malleable alloy. There is a demand for stronger, harder alloys, and a recent development in the USA has tried to address this concern. The alloy they developed is a 92.5% silver, copper, palladium, tin, zinc composition containing 2.75% palladium. This new alloy is much harder than conventional sterling silver, with an as-cast hardness of 90 to 110 Vickers compared to 65 for conventional sterling, and can also be age hardened up to about 140 to 170 Vickers. It also has a superior tarnish resistance. I will note here that 925 sterling silver dominates the UK and many other markets, but in other markets, lower fineness of silvers, typically 800, 830 and 850 are preferred. Let's move on to platinum. Platinum only became popular in jewellery in the 1970s, when the market was promoted by the platinum producers through the Platinum Guild International. Up to this time, most jewellery alloys were based on the industrial alloys such as platinum iridium, platinum ruthenium, platinum gold and platinum copper, with alloys for jewellery manufactured largely at 950 and 900 fineness, although 850 and 800 finesses were also in use in some markets. All these alloys have high melting temperatures, making manufacture of jewellery, particularly investment loss wax casting, difficult and challenging for the jeweller used to working with gold and silver. There was very little development of jewellery-specific alloys at this time, although the platinum 5% cobalt alloy for investment casting and the age-hardenable alloys containing gallium, such as platinum 3 gallium, 1.5 indium, were developed and introduced commercially at that time. An advantage of gallium and indium additions is that they lower the melting temperatures, and their use will be seen a little later in some other later alloy developments. At the end of the 20th century, the platinum jewellery alloys in common or growing use around the world, and their application was summarised in 1996 by Huckle of Johnson Matthey and in 1999 by Mertz of Platinum Guild International. And the link to their industrial alloy origins can clearly be seen in this table. And I hope you can all read it. I know the type is a little bit small. It is evident from looking at this table that at 950 and 900 finuses, there is a broad range of alloys available with varying mechanical properties, each suited to various manufacturing techniques. In general, the working of platinum alloys is not a problem, although polishing and machining is more difficult compared to gold and silver, and the low thermal diffusivity of platinum and its alloys makes laser welding and additive manufacturing easier compared to gold and silver. The major issue in manufacturing has been investment casting. The high melting and casting temperatures required use of special phosphate-bonded investment mould materials, and the poor melt fluidity requires use of centrifugal casting machines to obtain good mould fill, rather than the modern gravity machines commonly used for gold and silver. The new generation of tilt casting machines are also suitable. The chief problem with platinum casting is getting defect-free castings, and there have been several investigations on the relative merits of different alloys, looking particularly at surface quality, form filling, and gas and shrinkage porosity. The general findings from these studies show that the platinum 5% cobalt alloy to be the best of the current alloys, but it is still not an ideal alloy. Let's move on to carat gold alloys. Gold jewellery, as I'm sure you all know in this room, can exhibit a range of colours, and hence a range of compositions exist to cover this colour range at all the standard caratages, and that ranges from 8 to 22 carat, used around the world. To understand why there is such a large range of caratages on the market, one needs to understand the markets around the world and the impact of culture on caratage preference. I'm not going to go into that now, but there is a reference if you're interested. So let me start with the normal coloured golds. Gold is unique amongst the precious metals in that its alloys can be made in a range of colours, depending on the alloying metals used, as well as the intrinsic rich yellow colour. Alloying it with copper moves the colour towards pink or rose and to red, whilst alloying it with any other white or grey metal tends to bleach the yellow colour towards white. Alloying with silver and cadmium gives a greenish hue to the yellow, and such alloys are often referred to as green gold. As noted earlier, the coloured carat golds are based on the gold-silver-copper system, often with small additions of zinc as a deoxidizer and to improve working and form filling during investment casting. They may also contain small additions of grain refiners such as iridium, ruthenium and cobalt to reduce the grain or crystal size, and the colour variation from pale yellow through yellow to pink and red is achieved by varying the silver-copper ratio. Very small silicon additions may also be used as a deoxidizer, giving clean surfaces on castings, but note that too much can lead to embrittlement of the alloy. We look at white golds. At low caratages such as 8, 9 and 10 carats, alloying gold with just silver yields a good white colour, but such alloys are soft, and many commercial alloys of these caratages may contain some copper to increase hardness, to the detriment of the whiteness. At 14 and 18 carat, there are two classes of white gold where nickel or palladium are used as the principal bleachers of colour, with additions of copper, silver and or zinc used to modify the mechanical properties. In many commercial alloys, the amount of nickel or palladium is limited for technical or economic reasons, and the alloys are often not a good white colour. And there's a good example on the bottom of this slide. Here, the rhodium plating's been removed, and you can see quite clearly that the alloy is not a good white colour. Jewellery in such alloys is often rhodium plated to confer a good bright white appearance, and this posed a dilemma to the industry in terms of defining the boundary between yellow and white quantitatively. This was resolved in 2005 by an MJSA World Gold Council task force, where a parameter, the yellowness index, was used to define quantitatively where the boundary between yellow and white lay. White golds have a yellowness index of 35 or less. And within that definition, there are 3 grades of whiteness. The concerns with many people becoming sensitized to nickel and suffering from a skin allergy led to the European Union imposing the Nickel Directive legislation in 2000 that restricts the amount of nickel that leaches out from jewellery that is in close and constant contact with the skin. The advent of the EU Nickel Directive that limits the use of nickel in jewellery and the higher cost and density of palladium has resulted in much research and development to find alternative white gold alloys. Alloying additions of manganese, iron and chromium, for example, have been evaluated, but have been found wanting on important aspects, such as a tendency to crack or to tarnish heavily. Basso and his colleagues at Legor have explored the use of gallium as a primary whitener, and recently Peretti and his colleagues have explored the use of germanium as the whitener. An interesting development has been reported more recently by Simonet, and she reports the development of a very white alloy. It's got a yellowness index of only 7, that is suited to manufacture by selective laser melting, and we heard a little bit of reference to that technique this morning. Thus, the alloy is only required to be made in powder form, and so some constraints imposed by conventional processes are removed. This gives some extra freedom in terms of alloy design. The alloy is an 18-karat gold containing 15% chromium with some palladium and iron. It has a lower density of 13.5 compared to a 15% palladium white gold, which gives economic benefit and is resistant to tarnishing and corrosion. It has a good hardness of 215 Vickers, rising to 480 or more Vickers in the age-hardened condition, indicating good wear and scratch resistance. So let's look at a few alloy developments that have had very limited commercial success. There have been several alloy developments over the last 30 years that have not yet found wide commercial application, although very interesting technically, and it is worth including these in the review. I will talk about high-strength, high-carat golds and silver and platinum, unusual colours and unusual surface textures. So let's start with high-strength, high-carat golds. High-carat golds, and we're talking 24-carat, 22-carat, 21-carat, are popular particularly in the Middle East and the Far East cultures. Such alloys tend to be soft, single-phase alloys, and thus jewellery is prone to heavy wear and deformation. There is a desire for such alloys with improved strength and hardness. There have been 2 technologies developed in the last 30 years to meet this need, namely 990 gold and microalloyed gold. These have been developed mainly for 24-carat gold jewellery, but the concepts can be applied to other high-carat golds. Both approaches are also applicable to strengthening lower caratages of gold and to silver, platinum and palladium. So let's look at 990 gold. The development of 990 gold dates from the late 1980s, and it is a gold 1% titanium alloy, i.e. 990 fineness, so it is hallmarkable as 24 carats. It has mechanical properties considerably superior to conventional 24-carat gold, approaching those of 18 karat gold, as you can see in the table. Whilst this alloy has attractive properties, it has not found much commercial interest, probably because it requires sophisticated alloying and manufacturing techniques in a market where cost is a priority and manufacturing capability has been relatively unsophisticated. I think we can say it was too advanced for its time. However, the concept of using titanium additions has been explored for both silver and for platinum, and more recently it's been developed for 22 karat golds for the Indian market, and I suspect that may be where it finds some measure of success. In the early 2000s, a number of micro-alloyed golds were developed. These are based on total alloying additions of 0.5 weight% or less, typically 0.3%, and even down to only 0.1% in some instances. And this affects a dramatic strengthening of the gold microstructure. Such small additions are approaching those typically used to control grain size. The basis is to add alloying metals with very limited solid solubility in gold, such that there is significant hardening by second phases. Typical alloying metals include calcium and the light rare earth metals such as cerium, lanthanum and dysprosium. This table lists some of these microalloy developments and compared at the bottom of the table to 24, 22 and 18 karat conventional gold. I'm not going to go into detail, but if you want that information, it will be on the JTF website. Significant improvements to 22 karat golds have been described using conventional alloying techniques. Van der Lingen and her co-workers at Mintec and Fischer-Bühner at FEM in Germany have both demonstrated use of circa 2 to 2.5% cobalt and antimony additions affect a significant strengthening. Taylor has also patented a cobalt-containing alloy, but with up to 1% boron included. However, the microalloying approach can be effective in 22 karat and lower karat golds too, with using small additions of gadolinium and calcium. Again, these stronger 22 karat gold alloys have not seen much commercial uptake to date, despite strong interest in the Indian markets. But I think that may yet change. If we talk about high-strength silver and high-strength platinum, the microalloying concept has also been applied to pure silver and pure platinum using small additions of the rare earths such as gadolinium, cerium and samarium, and that results in higher strengths and hardnesses. And on this slide I've given you some results for pure platinum and for pure silver. Pure platinum and pure silver are the trademarks. That's all I'm going to say on these materials. Let's move to unusual colours. There has long been an interest in unusual colours of precious metals. Some of these colours are intrinsic to the alloy and are based on coloured intermetallic compounds of the precious metals, and others are achieved by surface treatments and coatings. Gold has received the most attention, and so colours such as purple, blue, black and brown can be made. Some commercial success has been achieved, notably with purple gold, or amethyst gold as it's sometimes called, applied as a coating, and that is of a gold aluminium intermetallic compound, AuAl2, and the blue, black and brown generally applied as an oxidation of the alloy tailored in composition with additions such as cobalt. Some coloured intermetallic compounds of platinum and gold have been used to form pseudo gemstones marketed under the Platigem label with colours in the range pink, orange and yellow, but they again have not achieved commercial success. And lastly, let me talk about unusual surface textures. Intermetallic alloys in the gold, aluminium, copper system show a quasi-martensitic transformation which results in a colourful sparkle effect on the surface. Marketed under the label Spangold, they were developed by Mintec in the 1990s at 18 and 23 karat gold content. But again, they have not found commercial interest. So that's all I'm going to say on what's happened up to now. Let's have a quick look to the future. It is evident that the precious metal jewellery alloys have become more complex and more precise in composition to optimise properties to meet manufacturing and market needs. We note that over the last century, alloy compositions are being tailored to suit specific manufacturing processes, to obtain improved performance in service with the customer, and to meet the latest market and legislative demands in terms of quality, health and safety, and appearance. Cadmium and nickel are good examples of metals now limited or banned for health and safety reasons, and this has led to new alloy developments, including a range of cadmium-free solders and, we mentioned a bit earlier, the white golds. The irritation of fire stain and tarnishing has led to improved silver alloys. The problems in casting, particularly the incidence of porosity, has recently led to the development of improved platinum casting alloys. Oops, sorry, press the right button. This table lists some of the recent developments in platinum alloys for casting, and we can expect to see some of these achieving some commercial success. And this is just a table that summarises the range of platinum alloys that have been studied in casting trials since 2000. You will notice not only some of the conventional alloys that we saw in the earlier table, like platinum 5 cobalt and platinum 5 ruthenium, but there's also a range of new alloys containing gallium and indium, usually ternary alloys, and one or two there where we don't yet know what the magic addition is. So there's a good example of progress in alloy developments going on at the moment. I'm now going to turn to additive manufacturing, and we've already heard this morning a couple of papers on one particular technology, or two particular technologies, because Frank also spoke about additive manufacturing. New manufacturing technologies also impact on alloy development. More recently, the advent of additive manufacturing, or 3D printing, by selective laser melting of precious metal alloy powders to produce near-net shaped jewellery, has shown that alloys need to be tailored to suit the process. High vapour pressure metals, such as zinc, are not desirable in the composition. And we've already mentioned the new very white gold alloy, which was developed specifically to use by additive manufacturing technology. Others have also noted that alloy compositions need to be changed for selective laser melting. For example, in sterling silver, to facilitate better consolidation, reduced porosity of the alloy, as described by Fischer-Bühner, and the use of additions of alloying additions such as germanium iron to lower thermal conductivity and reflectivity in 18 karat yellow gold has been demonstrated by Klotz, and we're going to hear from Ulrich again later this afternoon. As noted earlier, platinum alloys have inherently low thermal conductivity, and so tailoring of composition of platinum alloys for additive manufacture don't appear to be required. Alloy development is also in a new phase. No longer is the old trial and error approach appropriate for rapid development of improved alloys, even if conducted in a structured way. The new alloys by design approach uses algorithms based on the latest science, proprietary software, and computing horsepower to predict the theoretical performance of millions of different alloy compositions simultaneously and to choose the best optimization for a particular application. This approach starts with a lot of basic data on various properties and alloying behavior, which is fed into the scientific computer models and allows the modeling of performance of different compositions and hence optimization to suit the application requirements. It will be interesting to see how this approach impacts on improved jewellery alloys. Obvious applications would be improved strength 22 karat gold alloys and other high karat gold alloys, and improved strength sterling silver alloys with fire stain and tarnish resistance, and its use to develop improved platinum casting alloys has already been reported fairly recently by Glatzel and his co-workers in Germany in 2018. There are two areas of novel precious metal alloy development that are at an early stage of research and development, and these have yet to be commercially exploited in the jewellery industry. These are bulk metallic glasses, otherwise known as amorphous metals, and shape memory alloys. This may be due to the industry being unsure of what benefits such alloys could bring to jewellery and their manufacture. Just going to say a little bit about bulk metallic glasses. You're going to hear a lot more shortly, and I won't go into too much detail. These are alloys that do not solidify into the normal crystalline structure, but to an amorphous structure when rapidly cooled. The alloy compositions generally are close to deep eutectic compositions, and solidification to the amorphous state requires rapid solidification. This amorphous or glassy state is metastable at ambient temperatures, and the alloy will crystallise above a critical temperature. The interest in such alloys lies in their unusual properties, such as high strength and hardness, large elastic strain limit, near zero shrinkage on solidification, and good processing capability, namely casting and thermoplastic type deformation, which enables substantial forming to complex shapes. And a couple of examples, they're shown on the next slide, I think. The casting of jewellery, a number of precious metal alloys, gold, palladium and platinum based, have been developed. In particular, two alloys suitable for jewellery application have been developed by Lo Wong Wutana. One is an 18 karat gold alloy of gold, silver, palladium, copper, silicon, and the other is an 850 fineness platinum alloy, platinum, copper, nickel, phosphorus. The casting of jewellery items in gold, bulk metallic glass, has been studied by Klotz and Eisenbart, and they showed that gold BMGs can be cast into complex shaped jewellery products. They also showed such alloys have a good white colour, but a drawback was that the alloys tarnished rapidly. Further progress on such alloys will be presented later today by Owen Houghton and Ulrich Klotz, so I'm not going to say any more about those. But let's turn to the other area, shape memory alloys. These are a class of alloys that can be heavily deformed in shape, but when heated above a critical temperature, return to their original shape. They also exhibit superelasticity, that is, large elastic strains when deformed above a critical temperature. Many shape memory alloys are intermetallic compounds, and gold-based shape memory alloys have been discovered. For example, ternary gold, copper, zinc alloys and gold, nickel, titanium alloys, where some gold replaces nickel in the well-known nickel-titanium alloy nitinol. Such gold shape memory alloys have some drawbacks, such as poor cold deformability. There is scope for more alloy development to produce better alloys. Question: how can one use the shape memory properties effectively in jewellery design and manufacture is an issue I think has yet to be defined. Use for mounting gemstones has been suggested, and the possibility of using them to join components together, as nitinol was originally used for, must also be considered. Platinum-based shape memory alloys have also been researched. This could be an interesting field for further research and development. to develop better precious metal shape memory alloys and explore the potential for jewellery application. I note we are in an era of smart materials, and there may be a niche here for shape memory alloys for use in smart jewellery. Right, you'll be pleased to know we're nearly at the end, so let's start making some concluding remarks. In this presentation, I've explored the development of precious metal alloys for jewellery application through recent history to the present day, with some comments on possible future developments. Our industry has been inherently conservative in outlook about the use of new technology, but there is no doubt in my mind that jewellery alloys have become more sophisticated over time and tailored to suit particular manufacturing processes, as well as improved consumer performance. We have seen alloys tailored for better castability in investment or lost wax casting, for improved tarnish resistance, for easier wrought fabrication, and now for better use in additive manufacturing technologies to produce net-shaped components. Here, in additive manufacturing, the major requirement has been to lower reflectivity of the powders and lower the thermal conductivity to enable a more efficient heating and melting. I've also attempted to look a little bit into the future. In current applications in jewellery, there's still a need for improved alloys with better consumer performance, such as stronger alloys and improved tarnish resistance. Possible new alloy developments, such as bulk metallic glasses and shape memory alloys, need further exploration. It is likely also that future health and safety legislation may impose more constraints on alloy compositions and stimulate further alloy development, as we have seen with nickel in white golds and cadmium in solders. Market demands may also have an effect, for example, a wider palette of colours or special surface effects. We are also in an era where ethical sourcing of raw materials, sustainability and responsible manufacturing has become increasingly important, and we shall hear more, I think, on this topic later today. Corporate social responsibility is a significant factor today. How this will impact the jewellery industry and the alloys we use in the future is not yet clear. And lastly, I'd just like to acknowledge many friends and colleagues in the industry for their support in providing information, allowing me to use their data and figures. I also thank the staff at Legor and at the Vicenza Fair for inviting me to present once again and for their kind hospitality. Thank you very much.
Thank you very much for participating as a speaker, Chris. And now we move to another Chris, whom we have for the first time the honor to have as a participant. Chris Plouffe è un maestro.
Chris Plouffe is a master jeweler and owner of the Chris Plouffe Designs at Leominster, Massachusetts. Among the jewelry techniques for which he is very well known are Mokumagane, which is going to be the focus of his presentation today, and Damascus steel working. He is in the industry from the beginning of the year 2000. His work has led him to consulting projects all over the world, as well as multiple awards from the Santa Fe Symposium, and he also has gathered countless mentions in various trade publications. He's going to focus on Mokumagane process. From the beginnings of feudal Japan to its use as a jewelry material by modern smiths around the world, Mokumagane is a demanding technique that even those well-versed in jewelry metals struggle with. This presentation will illustrate the beginnings of Mokumagane and the techniques used daily by two of the most prolific makers of quality Mokumagane in the world. The scientific method will be stressed rather than scientific testing. This paper and general jewelry skills will allow you to make Mokumagane like the experts. This is this promise. We hope this is true.
Thank you very much. Actually, the honor is mine. I visited JTF, I think about 10 or 11 years ago, and realized that I would love to be asked to present. So thank you very much for the warm welcome. A little less science maybe in my paper, a little bit more practicality. I apologize in advance if you expect more science, and if you expect more practicality, well, you'll get exactly your wishes. There we go, excellent. So it's a brief view of the history and how mokumegane is currently made in production, especially in my shop. And you saw on the first slide the mention of Jim Binion. He's a co-presenter, or sorry, co-author of this paper with me in 2016. We've actually changed a few things and improved upon some of the knowledge here. If you want to see more, I believe the paper will be on Legor's website. Okay, we'll be on Legor's website, and you'll be able to read more. This presentation is designed to be more of an adjunct to the paper, so it does not have all the technical information, but you can find things like times and temperatures in the paper itself. So mokumegane is 3 or more layers of non-ferrous material that have been bonded together, not using any solder or anything, using a solid state or liquid phase bond. The resulting laminate then gets manipulated to create a wood grain patterned material. So it is not layers of material that involve solder. This is not metal that has been soldered together. It's not precious metal clay, which some people describe as mokumegane. It's not Fimo clay, not polymer clay, not marriage of metals. Granted, you can create a similar pattern of mokumegane, but true mokumegane is bonded without use of any solder and is not any of these other materials. The beginnings of mokumegane are credited to a man named Denbei Schwami in 1658, born 1651 to 1728. He's a historically important figure in Japan, working in the Akita prefecture as a sword furniture maker. So he's not making samurai swords, he's making all of the parts that actually go onto a samurai sword that are made out of metal. And there's a few of those. There's the suba, which is the hilt guard. There's the collar that holds the suba in place. And then also you have the pommel or the fuchi of the sword. The first billets were made in a charcoal forge, and very little has actually changed in Japan with the way they manufacture their mokumegane. The first pieces, though, weren't truly mokumegane. They were actually designed to emulate a technique called guri or guribori, which was a laminate of paint, essentially, that was then carved through. It emulated this metal that they're making is trying to emulate this lacquerware, this guri or this guribori. But once it's carved, when you flattened it, they noticed they got a wood grain effect. So some historical examples of guribori. This is an 8 centimeter lid of guribori, and as you see, when we look at it a little deeper, you can see the details and you can see the layers. Actually, probably easier for me to see here. You can see the layers right there especially, but those layers are layers of different color lacquer that have been cut through. So it was also used for things like inro and nitsuke. This inro is the larger part here, and that's your traditional pocket that you would be wearing in the 1780s, 1790s in this time frame period, even a little bit earlier. And this is all made with that same lacquerware tradition that they then emulated to make out of metal to make mokumegane. This is a very important table. This is actually quite a nice historical example that sold at auction some years ago. This was made in about 1750. Sold at auction some years ago for what would be over 300,000 euros for a table that's about this tall, maybe, so small end table. But this is the initial inspiration for mokumegane that Denbei Schwami used to jump off into his next steps. So on this side here, you see a true example of mokumegane, and this is material that has been patterned and then flattened, so you can actually see the wood grain style pattern that's coming into it. And next to that is a close-up of a guribori tsuba, and you can see those layers really clearly in here. This has been patinated for a better look, but it's speculated that the reason the technique originates in Japan is you have some of the most skilled metallurgists and also patina patination going on right. I'm very nervous for some reason. I usually don't get nervous when I present. I apologize. Deep breath. You have a lot of very skilled metalsmiths that are working, and they're actually developing these alloys, and they're then patina them and making beautiful items out of them. And we end up with this turning into this diffusion bonding, this liquid phase diffusion bonding. So the no known historical examples of the same style of this bonding of non-ferrous materials are existing outside of Japan until possibly the late 1800s or so, but we weren't really sure until more research was done. Closest similar example happening in Europe at the time was in England, and it was Sheffield plate, but it wasn't developed for beauty. It was developed to save money. It was developed to maximize the price and minimize the silver used in an object. Another example at the time frame that looks very similar to Mokumegane is a central link of the chain of offices made for the mayor of Preston, Lancashire in the United Kingdom by Sir Alfred Gilbert, and that's in about 1887 or 1888 when this was manufactured. But we now know this was soldered, so it's not a true Mokumegane. This is more marriage of metals. And also Tiffany and Company had a lot of interesting things going on right about the same time frame, but we'll get to that in a little bit, towards Mokumegane. But really what happened in the 1970s is Mokumegane came to the US. Eugene and Hiroko Pijanowski, they were on a trip to Italy and they happened at a department store and saw a beautiful raised vessel that was made out of Mokumegane. And they found the artist that made it. His name is Gyokime Shindo, and they located him, as I said, and two of his contemporaries, and they asked Gyoke to teach Mokumegane to the West, and he flatly refused. He said, absolutely not, I will not do that. But luckily for the world, Norio Tomogawa was willing to share, one of his contemporaries. And this is Norio Tomogawa here. This is taken about 2008, and he's working on a piece of Mokumegane there. You can see right here he's got a large disc that he's patterning. And he's the teacher of Mokumegane to the West. He's why we have good Mokumegane technique that was brought to the West. So the Pijanowskis taught at a university level in the US, and they taught many, many workshops. And these early teachings mushroomed into the modern Mokumegane movement. And since really the mid-1980s, there's been a large resurgence with a lot of metalsmiths experimenting with the technique. It's practiced in many places now. You can find very good work in very fine jewelry stores. You can find very bad work in other places as well, too. There's good and bad Mokumegane. And in the US, we have at least 4 companies selling unpatterned material. If you don't want to go through the lamination process, you can just purchase raw materials that you can then pattern yourself. But we're going to go back a little bit into Japan, just for a view of some of these early works that led us into Mokumegane. So this is a beautiful example of one of those subas, the sword hilt guard. Very similar to the type Denbei Shwami would have created in the Guri style. This is unsigned by the maker. It's in a private collection. It used to be in the New York Metropolitan Museum of Art, but was purchased by Evan Yerman from David Yerman Jewelry. And I was lucky enough to see this when I went for a visit. And you can really, again, clearly see all these layers in the Guri Bori Tsuba. Another beautiful, beautiful Tsuba made in about 1740 by an artist, Masaka Takahashi. And this is a very early Mokumegane Tsuba. This is where you truly see Mokumegane. We're not looking at raised, or cut out areas. We're looking at the flattened metal that's had some applique put over it. This is called the Tsuba with a hawk and a sparrow. And it's in the Walters Art Museum, which is in Baltimore, Maryland in the USA. But you can see that the size of this would be about 100 to 110 centimeters across, in each direction. It allows for a wonderful palette, a larger place to use this Mokumegane for decoration. This is another beautiful, beautiful example here. This is actually sheet wrapped around a core, and they actually have even gone to the trouble. These are about maybe up to 9 centimeters in thickness. But they've actually, on all these sides, they've fitted metal to it, and there's a solder seam that runs all the way around, top, bottom, even on the insides. But this is a very special piece. This is actually combines 2 styles of patterning. There's a patterning style, and we'll show this a little later, but there's a patterning style here, and then these little parts here actually have another patterning style that has happened with them. And basically, these are designed to look like plum and cherry blossoms. Well, this is designed to look like flowing water beneath them. So very beautiful early piece. And another historical piece, I mentioned the fuchi, the collar of the sword, and then the kashira, the pommel, and you can see the guribori here as well. So later pieces, these would be from about 1920 maybe. These are sake cups designed for export. So if you're visiting Japan for tourism, this is what you would be sold at a department store at the time. And they're very interesting pieces. They're actually joined with pitch, much like early American silversmithing was done, where they're taking and using maybe an iron fork tines and joining it to a silver handle. But very interesting construction. Here's a shot that shows the signature and really shows a close-up clearly of the mokumegane here. Yeah, so you can see all the beautiful patterning that's been done on that. So this is a detail of the carving that Norio Tomogawa was working on. This will be hand-forged and hand-raised into a vessel. We're getting into modern times now, 1990s, 1980s even. These billets are still bonded in the traditional manner, that liquid phase bond in a charcoal forge. They'll stack, this billet itself is copper and silver, copper and silver, copper and silver. They'll literally tie it with wire. They'll put it in the fire and they'll observe it very carefully. And when the silver starts to almost run and almost get to that melt state, they'll actually remove it very quickly, strike it with a hammer, and that sets their bond. We're going to explain something a little different about the way we do things. But little has changed in Japan. Still the same way they're making things with these liquid phase bonds. So here is Norio Tomogawa actually raising that vessel in traditional work clothes and traditional work posture. And I've included the slide because even though he's the man who helped the West make the first mokumegane, he's not known for his mokumegane in Japan. He's known for his tsuiki form, and tsuiki is when you're making your raised vessels in Japan. He was declared a national Japanese living treasure in 2010. But I think when we look at his work, we can also say he's fairly a master of mokumegane. He does very beautiful job with mokumegane and even his patinas on his vessels. This vessel here is about 23 by 21 centimeters, hammered silver and copper with mokumegane and patinas. And so the mokumegane is silver and copper, and he's selectively applied patinas to get the multiple colors that he has there. Another one, this is about 15 by 18 centimeters, a lidded jar. This is from 1991. Again, beautiful technique, both in the raising but also in the mokumegane. And one more Tomogawa piece from 1997, hammered silver, copper, and shakudo, an alloy of copper and gold. And very beautiful work, about 22 by 23 centimeters. So we have mokume with a question mark. I wanted to go back to Tiffany. And when we first gave this paper, but these samples are too important to take out, but I'll steal the surprise and say they weren't true mokumegane. They were all done with solder. So these are all soldered laminates. But in the about 1870 timeframe, Edward C. Moore becomes the chief designer and head of the silver department at Tiffany and Company. He experimented a lot with metallurgy, brought a lot of things to Tiffany and Company, and personally, he had traveled to Asia. He had some pieces of mokumegane in his own private collection. They're now in the collection at the Metropolitan Museum of Art. So there was always a debate, is this being done with solder? Is this being done with diffusion bonding of material, whether solid state or liquid phase? And no one really knew. Some people suggested that they even brought craftspeople over from Japan to make this material for Tiffany. We couldn't find any evidence of that. So in 2016, when I presented, we didn't have an answer, but if we fast forward to now, I have a friend who works at Tiffany in their hollowware department and got access to the notes that they used to make these pieces. And unfortunately, we do now know that these are not true mokumegane. They are marriage of metals, as I said, soldered together, solder between the layers. Still wonderful pieces, though, and the real important thing that we have happening with Tiffany using these materials is they're bringing an awareness. Sorry about that. They're bringing an awareness to these materials in the late 1800s and early 1900s. So that first piece, and I don't know why I don't have an animation, but they're using very small little accents early on because they're struggling to make big pieces of this, is my guess. So these are some of the earlier pieces from Tiffany & Co. that are helping bring awareness to mokumegane and a desire for it. This is a little pocket pistol here that's beautifully engraved. I mean, the engraving itself is incredible, but there's a little bit of mocha megane there. So, you know, very interesting, that little inlay. We'll get a little close-up of it here. Yeah, you can see the mocha megane pattern on that, but a very interesting early piece from Tiffany. And then Tiffany started to do some larger pieces. This is mocha megane cigarette case and also the match case that they made. Some larger pieces that start to be a little bit more significance. And then in 1878, for the World's Fair, Tiffany produced a whole tea set of mocha megane. This was largely done with panel construction. They weren't forming it like Norio Tamagawa does. They were actually sort of rolling it around and soldering it and adding a base to it. But again, it brought a lot of awareness at this time frame, you know, starting, you know, in 1870 and moving forward in the United States of the art form. So here's a different mocha cup from Tiffany. And this is a silver mocha megane match case as well. This would have been from about somewhere in the 1880 to 1890 time frame, about 6 centimeters high and, you know, interesting, very fine-grained pattern. They made ice cream spoons because everyone loves ice cream. And there's a close-up of the handle of that. Another match and cigarette case made by Tiffany and Company that's in New York at the Metropolitan Museum of Art. It's a close-up of that case. And here we have one of my favorites. I don't know, it's just very visually stunning. This is about 5.7 centimeters high, an ounce of material, and it's a match case again, with just beautiful lamination and beautiful manipulation of that pattern. Very simple pattern, but very stunning, very crisp. And probably of the most significance made in this time period, Paulding Farnham was actually a protege of Edward C. Moore, and his family owned a silver mine, actually silver mine that was a copper silver mine. And they used the material from this mine to actually make the mocha megane to make these vases. And these were significant. There were 2 made. They're about this tall. And unfortunately, one of them was converted to a lamp and had a hole drilled in the bottom sometime in the 1900s. Terrible waste because they're really, truly one-of-a-kind pieces. But now to the method. So we have our history. We have the beauty, we have what inspires the makers to make, and now is the modern method used in manufacturing mocha megane today. So Jim Binion and I both practice this method in our shop. We make, my company actually has the pleasure of making mocha megane even for some other large companies. We manufacture the mocha megane that Hoover and Strong sells in the USA. You know, these are our practices. There's many ways to make mocha megane. You can use the liquid phase bond method. You know, I'm not suggesting you have to clean or do things exactly this way, but this is the way that we've found success in a small studio. And this is also for a solid state diffusion bond. It allows for very excellent repeatability and also for production. The problem we've always found with a liquid phase bond is as you do that bond, you can get some very muddy layers where the 2 materials come together. And this technique allows for quite crisp lamination. It begins with cleaning and inspection. And I always say the 3 most important things when you make mocha megane are cleaning. 1, number 2 is cleaning, and number 3 is cleaning. So you have to do a very good job of cleaning the materials. We inspect all of the materials when they come in from our supplier of golds and other precious materials and even non-precious materials for any defects, gouges, blisters, anything that's going to cause a problem and that will interfere with our lamination. And from there, we're going to give an initial cut down. We use Scotch-Brite mounted on a motor, and we actually will cut down the material, then clean and distilled or deionized water with a very small amount of a neutral detergent. You don't want anything that has any hand lotions or anything mixed in with it. If it's a dish detergent that says it will keep your skin soft, it's probably not good. So we use just like Simple Green in the US. It's a very clean detergent without any extra additives, but you only add a very little bit to the first tub. The second tub here is actually for rinsing off. After you've soaped and scrubbed, we rinse off. And then we're holding it in this tub. And in that tub, to prevent any oxidation, we've added just a little pinch of citric acid to help prevent any oxidation while it sits. So we're scrubbing the sheets by hand. And here's a little short movie that actually will show you the process. And I guess when I say short or brief, it's not that brief, but it's very, very important to clean the material thoroughly. So we've cut down across it in the power machine. Now hand scrubbing, and we'll hand scrub it in 4 directions. After it's hand scrubbed, that's when we can rinse it off, and then we can put it in that holding tank. And every sheet goes through this process. And we really have a minimum of about 19 sheets, sometimes as many as 45 sheets in our lamination. So it is time consuming and demanding. Many times people will ask, why is it so expensive? It's more expensive than 18 karat gold, and it's only half gold, half silver. And then you show them this movie and they start to understand. It's a time consuming process, but it's a very rewarding one in the end. So we then have to take some steel plates. We call these torque plates, and there's some bolts behind them as well. And we're coating these with boron nitride. A trade name for that in the US is welder white. But we're really looking for just anything that's going to keep the precious metal sheets from sticking to the torque plates. Because Mokame is great when it's all precious metal. When you have 2 big, giant, heavy steel plates stuck to the side of it, it's not nearly as good. So we hand dry the sheets. This is done with a lint-free cloth. And we also will wear an optivisor when we do this, just so we can give it a final inspection and make sure we don't have any lint stuck to it or any dust when we are stacking the material. We're going to carefully stack the material and alternate depending on what our lamination schedule is, and then load those onto the torque plates as you see there. This is lining up the stack. Those bolts are not tight yet, so we're just using a couple metal rulers to sort of get the edges as close as we can. We don't want to lose much. Mokame gane, a hard fact, if you do it correct, is 50% waste by the time you're finished. So it means that our refiners quite love us, but we want to get as much of a yield as we can. So once that's done, we'll tighten those bolts down, and we actually use a hydraulic press to clamp those torque plates tightly, and then we'll tighten the bolts. And then we need to get it ready to go into the kiln for the bonding part. So this is going to be placed into a foil bag. So this is just stainless steel foil that we've, 316 stainless steel that we're making a bag out of. And it's just big enough to allow the torque plate to slide down into the inside of it. So once we put that in the bag, we actually are going to add a small scoop of charcoal. So just activated filter charcoal like you'd find in a filter. In a pinch, you can even just use like charcoal like you would grill with, just break it up into small pieces. This is to create a reducing atmosphere inside of that bag while we're bonding. We close the bag, we put it into a preheated kiln, and we go away for a few hours, generally 2 to 4 hours, depending, and generally the temperature, I apologize, I'm terrible at Celsius to Fahrenheit conversion, but it's in the paper, the proper Celsius temperature. For silver laminates, it's 1350 Fahrenheit. For gold laminates, we're around 1450 Fahrenheit. So the bag gets removed from the kiln and then carefully opened. And you can see it's still quite hot there. We'll place it back into the kiln to get it back to temperature, and then we're going to do a hot press. We have done a bunch of research, and you can find it at santafesymposium.org on processing Mokame gane and how to make the strongest materials that you can have. And we found that this hot press is very important. So we reduce about 20% in this hot press, and you can see we're partially through that hot press because the bolts have dropped down, and we're actually actively hot pressing. And we usually will repeat a hot press at least once. Especially if it's a bigger billet, just a fast way to get a quick reduction that we can then start to cold work. So we're going to hot press, and then we need to go to cold press. You know, we're lucky we have a bunch of equipment hanging around. This is a big 450-ton press, but you can do it by hand. There's no reason why you can't use just an anvil and a hammer and forge it down to a size that will fit in the rolling mill. And we found that's the biggest limit making this in a small jeweler shop, is most rolling mills don't open very wide that you're going to find in a small shop. So you have to do a fair amount of reduction, but it's also quite good for it. So we'll go through a series of annealings and forgings and annealings and forgings until we can get it into the mill. And we generally only reduce 20% from the starting thickness. So say if we started with 20 millimeters, we're only reducing to 10 millimeters in 20% increments. Then we can actually start to reduce a little further, 30 to 40% at a time before we have to anneal again. So here's a billet. Once we have it all bonded, we'll call it a billet. This one has been trimmed to show you clean metal. One of the things I mentioned, the 50% loss, the big problem we have is when we stack it, it never looks this pretty. It looks all, edges are sticking out. You have to, in order to make good material, and you can test me on this all you want, go home and try this or have someone try it. If you don't remove at least all of the material to clean metal plus 2 millimeters, your billet will really, you'll struggle with getting it into sheet or into usable material. You just have to get rid of any possible contamination that's come in from the side of the billet while you were bonding it. So for sheet, we generally will roll that billet then at this point. We're lucky, we have a rolling mill that opens up to about 50 millimeters, so it's very handy for us. But we'll roll this to around, for making sheet, about 5 millimeter plate. So however big by 5 millimeters. And then we can start our series of cuts and deburring and annealing and rolling steps until we get the desired thickness. For making figural patterns, for those really, some of those early examples you saw with lots of activity in the pattern, we'll probably have about 45 layers, as I mentioned. We want a lot of layers to get some beautiful patterns. So this plate here, this is about 5 millimeters, would be one of our first patterning. We started to make our cuts, and you can see the layers in there. This is just done with a round ball burr. But one of the most important things between your patterning steps, and generally I find to make a really beautiful wood grain figural pattern, I'll pattern once and then reduce a millimeter, then pattern again and maybe reduce again until we get to the desired sheet thickness, is you have to deburr it. So these are just two wonderful tools I've found for deburring, and they're manufactured by 3M in the USA, and I think fairly readily available around the world. And it's just a radial bristle disc that's very coarse grain, and it helps to take off any of the burrs. If you don't remove the burrs, they get folded in the material, and then when you manipulate the material later, they want to pop up and you're left with voids and all sorts of nasty problems to fix. This is some beautiful pattern sheet here. This was made by Jim Binion, co-author for this paper. Jim and I also own our own companies and a separate company together called Laminated Metals Technology. There's about 35 layers in this pattern, and this is copper, nickel, and brass, actually, and just a very beautiful figural wood grain pattern. This was joined into a sphere. That was a gift for someone, but you can see the, yeah, right there. You can see the solder line pretty clearly right there on this. That's one difficult thing, is how do you match the pattern together? Always been a problem. But this is really where my company specializes. We manufacture a lot of mokumegane rings. And we do this with forging rod. And this here is what I would call forging rod. So about 75 millimeters in length, and this is right now 6 millimeters square. So to make forging rod, we're back to our billet, and we have to divide this billet into equal portions. In order to make a rod of material, we don't want to try and turn something that's a rectangle into a square. So we'll actually cut this billet down the center, and then we'll actually cut it again, or cut it down the center, creating that square shape. And once we have that square shape, we can actually go on to the next step. We learned a few years ago, actually maybe about 10 years ago, one of the problems with rolling mokumegane is it's under a tremendous amount of shear force as it comes through the rolling mill. So you would always have at the very end of the billet, it would actually fail and it would come apart. So we just started simply taking a piece of silver, and it's really scrap silver from our other processes, and just soldering it to the end, trim that edge off, the overhang, and then we can roll it, and you don't have that, it doesn't want to come apart with that shearing force. So then we're going to roll it, and we're going to go through steps of rolling and annealing until we reach the needed size. And generally where I start making rings is at about 5 millimeters. So this piece here that's in the vise is about 5 millimeters square by about 100, or it could be longer, millimeters. but we have to do something to make the pattern convincing and exciting. So for a really great wood grain pattern, the easiest way to do it is to twist. So this is a piece that's been twisted, and we just grip the other end in pliers and twist it until we have enough twists per centimeter. And then we'll actually take that, and you can see the flat spots. We've just rolled it a little bit back through the rolling mill just to give us a bit of a square shape. So once we have that square shape, we can start patterning and carving for mokumegane. And we never cut more than a third of the way through mokumegane. It doesn't matter if it's a ring, it doesn't matter if it's sheet metal. If we cut further than a third, we probably will end up with problems moving forward with holes in the resulting laminate and where we're trying to get. We're very careful, obviously, when we carve mokumegane. This is a little matte wax box. It's barely big enough to put your hands in, but it works in a pinch. But what we really like to use for carving our mokumegane is we have just an old polishing hood that we've repurposed. And this is a micromotor here, so 40,000 RPMs. It's much more effective to carve at higher RPMs than a flex shaft. A typical flex shaft will allow you to do so. So we just do all of our carving in there, and you can see all of the precious metal dust that's in there. We want to be careful to capture all of that, obviously. So this is actually a piece of material that we've patterned. So you can see the twists right here, here. And you can also see some cuts on it. And what we've done is we've cut across the grain. So where those twists are, we're cutting across the grain. And I use a round edge wheel burr to do this, or you can just use a round burr to do it. And this type of approach, when you cut across that, will actually give you a beautiful wood grain pattern, as you can see here. So that patterning technique is what yields this in a ring when you flatten it. So this is palladium 500, an alloy of palladium and silver with a little bit of copper. That's the dark color, the gray. And then either 18 karat yellow gold or 14 karat red gold with silver is the white. This is another favorite pattern. In the US, we often call it baby's first mokumegane pattern because it's very easy to make. And the one problem with it is it doesn't necessarily show a lot of skill of the maker. It shows a method, but not necessarily skill. We have taken that material, we've twisted the stock. You can see the twists here, of course. But the way that you make this pattern is rather than selectively applying a burr, you just drag your round burr all the way down the top of it. And you want to cut about between a quarter and a third of the way through it. And it yields those stars. So a very derivative pattern. Anyone in this room with the same round burr and the same mokumegane can create that pattern. But I love it still. It's one of my favorites, even though it's very simple to make. And there's results. So this billet here is 14 karat red gold, 18 karat yellow gold, and then this is 14 karat palladium white gold, the thin gray. And you can see the thin layers there compared to the width of the others. That's controlled by the starting thickness of the sheets that you use in your laminate. So once we're carved, and how do we get to the stage of the ring, we're actually going to flatten the material. So we anneal it. I find you can certainly hand forge it to flatten the material. I like using the hydraulic press. So here you can see just some press blocks here with the material in it, and we're just using the hydraulic press to form the material to get it ready to be made into a ring. So the carved mokumegane ring blank you can manipulate by further pressing or forging or carving even until you're ready, and then you can bend it and then we'll join it into a ring. One note about mokumegane, if you use it or make it, is you want to use a solder one heat level below where you think that you should be. You create an alloy when you bond these together in between the two metals that generally has a lower melting point than the constituent materials. So instead of hard solder, medium solder is recommended. So once you solder that ring and join it together using traditional methods, we finish it using traditional methods. This is 14 karat red gold, 18 karat yellow gold, and thin layers of sterling silver. And believe it or not, it's the same laminate for both of these rings. The only thing we've done to this one different than that one is etch the silver, to etch the silver away. It really makes the pattern quite different. So that brings us to the end. I want to say thank you very much for having me. This is a short video that sort of shows the whole process. It's sped up because if not, it would be a long video. But I hope you enjoy this, and I hope it helps you understand a little bit more how to make and work with mokumegane. Thank you. I should probably narrate and tell you. So we're cleaning and then we're pressing those torque plates. We're making the foil bag here, folding over the foil bag, goes into the kiln, our hot press, and then cold press and rolling, and then one of many annealing steps to get us from the 6mm by 6mm forging rod, twisting, more annealing, lots of annealing steps. Once we have the proper number of twists, this is where we'll carve, as I mentioned and showed. That deburring wheel coming to use, very important to remove those burrs, otherwise you end up with a disaster. And this is a final dimensional roll after we've pressed it, cold pressed it, once we've patterned it. And that's about where we want to start. 2.3mm is where we'll construct our rings. It's very thick for a ring, but I'll show you why. And preparing the ring blank for bending and soldering. And I'm just stick feeding solder because one of the methods we use is we're going to machine this ring so we can put a little extra solder. We'll sacrifice speed for saving money sometimes. Well, time is money, but... And then we hand round everything. And then we'll machine it to the proper width. So if we're making a 7mm wide ring, we usually start with an 8mm wide blank. And then the reason we start with 2.3mm thick is right here. That's actually putting a radius on the ring, and it really helps with the pattern development. And then just sanding the sides. We're in the finishing stages now. And we do much of our finishing at the bench. I don't usually use a polishing motor, stand-up kind. I find that it's better work is done sitting at the bench. And this is just going through the abrasive steps. We use Scotch-Brite to put the matte finish on the outside. And one of the things that we do, and I think it makes our finishes better, is it's tempting to stop once you get up to about 1,000 grit and go straight to Scotch-Brite. But we actually will go to a full polish outside and inside of the ring, then work backwards for the matte finish. That's an error. And then the last thing we do is every ring gets hand finished, and I saw a little dish soap I put on there, and it just makes the pad slide a little easier, and our results. Now I'm done. Thank you.
Molte grazie, Chris. Continuiamo, cambiamo.
Thank you very much, Chris. Now we're changing subject. Again, a scientific contribution. We're going to hear from Dr. Ulrich Klotzer. Ulrich Klotzer got his degree in physics and metallurgy at the Stockholm University. He has a PhD in material sciences at the Polytechnic of Zurich in Switzerland. He is the manager of the physics and metallurgy department at the VIM in Schweiz, Germany. The subject matter of his presentation is that of amorphous platinum alloys for jewelry making. This paper introduces a new class of platinum alloys with completely different features vis-à-vis the conventional alloys. Amorphous metallic materials for precious materials are very important for jewelry and watchmaking because of their scientific characteristics. Here we have the combination of microcasting with conventional coating. Having said as much, I'd like to invite Dr. Klotz here.
Thank you very much, Andrea, for the kind introduction. I'm speaking about bulk metallic glasses. We heard a little bit about it in the presentation of Chris Corti. And this is a work we did together with the colleagues at FEM in Stuttgart. And I recognized that I was speaking here in 2014 already about bulk metallic glasses, that time gold bulk metallic glasses, and this time I will speak about platinum bulk metallic glasses. Now I will first start with an introduction. What are bulk metallic glasses? We heard already a little bit, but I will go a little bit deeper into that. And we will have a second presentation after me by Owain, and he will also go into the physical metallurgy of the bulk metallic glasses, which is different from conventional metallic materials. Then I would like to explain the alloy compositions of bulk metallic glasses made of platinum alloys. These are special alloy compositions. I will show how we prepared the alloys and then how we made some jewelry pieces using investment casting processes. And of course, I will show you some jewelry examples that we presented. We had the chance that one of our colleagues was a master goldsmith, and he made these parts at FEM. So what is a bulk metallic glass? This diagram shows you the properties of metallic material as a function of temperature. And we see in the lower graph, this is the volume as a function of temperature, and the blue curve shows what happens with the melt when you cool it. When you reach the melting temperature, there is a sudden drop of volume during the crystallization, and this sudden drop of volume causes the shrinkage porosity that we know from casting processes. But bulk metallic glasses do not show such a sudden drop of volume. Instead, they show a continuous shrinkage until the glass transition temperature is reached, and after that, the volume change is even slower. So due to this continuous and slow change of volume with decreasing temperature, there will be no shrinkage porosity when cooling these alloys. Well, and the material is not crystallizing, therefore there is no crystallization shrinkage, but instead the viscosity of the melt, which is plotted here, is steadily increasing, and it's with decreasing temperature it's exponentially increasing, so the material gets somehow solid, although this structure, this amorphous structure, is still there. And we call this amorphous. Amorphous means there is no crystalline structure, and we also call it glassy because glasses, the conventional glasses we know, window glasses, also have this structure. But a metallic glass, of course, is not transparent. A metallic glass looks like a normal metal. So in order to reach these special properties, we have to cool very fast. And a second diagram here shows the temperature over the time, and this is plotted on a logarithmic scale. And it happens, it shows, this red curve shows what happens to the material when you cool it with this temperature time profile. So at a liquidus temperature, usually we expect the material to become crystalline, but when you're quick enough, you can avoid this the green area is the crystalline region. When you're quick enough, you can pass by this crystalline field, and the material stays amorphous, like in the liquid phase, and then at a certain temperature, the glass transition temperature, it gets to the glassy state. Now, most metals don't show this, and yeah, just this image is showing this amorphous structure. It's promoted by several atoms of different kind, this irregular amorphous structure. So most metals are not doing this. It's the effect of bulk metallic glasses is only known since the 1960s, because in order to pass by this crystalline nose, you have to cool extremely fast. So for a metallic glass, you have to have 100,000 to 1 million kelvins per second, which is extremely fast. And then you can only reach 50 micron thick material. But when you want to have it bulk, so massive, thicker, this has to happen at much lower cooling rates, only 100 to 1000 Kelvin per second. And then you can reach about 1 millimeter amorphous material, and then we call it bulk metallic glass. Now here are some critical cooling rates, we call this, that are required to form the bulk metallic properties. And we see that for gold-based bulk metallic glasses, we have 18 Kelvin, for platinum 2.5 Kelvin per second, and for palladium, we have only 0.16 Kelvin per second, which is quite slow cooling, and therefore we can reach really high thicknesses in this palladium bulk metallic glasses. Gold requires quite high cooling rate, palladium quite low, and platinum is in between. And just for comparison, if you quench into a copper mold, you can reach about 100 to 200 Kelvin per second as a cooling rate. So this is required for gold bulk metallic glasses, but for platinum, we hope to also do this by investment casting. What is important is to have a high purity of the melt, because all impurities will act as nucleation sites for the crystals, and so reduce the critical thickness that you can reach during quenching. Now, some properties of bulk metallic glasses. Why are they interesting, or what is special with their properties, is shown in this plot. This shows the strength as a function of the elasticity. And we see several groups of materials, steels, titanium alloys, so classical, conventional metals. They have high strength and a very low elastic limit. Usually we define 0.2% as the elastic limit in most materials. We see some non-metallic materials like silica, wood, or polymers. They have much lower strength, but polymers have really high elastic limits of about 2 to even nearly 3%. So this is, we know it, and rubber is even more. We know that the material is soft and can be bent forth and back without being deformed. And bulk metallic glasses show also very high elastic limit, quite comparable to polymers materials. So this is really unique for metallic materials, and this is therefore quite interesting, these very different properties. How can we use it? Now, to reach these special properties, we have to use special compositions. We heard in the presentation from Chris Corti that some elements are not really beneficial in jewelry alloys. For instance, high amounts of silicon, germanium, phosphorus. But especially these elements are interesting to make bulk metallic glasses, because what do these elements do and why they are usually critical? They form so-called low melting eutectic compositions. So this diagram shows sections of phase diagrams. So it's a collection of different binary phase diagrams, and it shows the reduction of the melting point by this element. So for instance, bismuth here at about 45%, reduces the melting point of pure platinum to only about 750 degrees. Now we want alloys with a fineness of ideally 950 platinum or at least 850 platinum, which can be hallmarked. And if we look at this diagram, we see that especially phosphorus, boron, and silicon are interesting. And with phosphorus, we can lower the melting point below 600 degrees C, which is, yeah, nearly 1,200 degrees lower than conventional platinum, which is extreme. So what Chris mentioned, Chris Corti mentioned before, the high melting point of platinum alloys is dramatically reduced. And of course, this is also interesting in terms of the processing, because some arguments that you have for melting and casting platinum, high stability of the refractories, etc., are probably not true anymore if you can lower the temperature that much. But you have to keep in mind these elements are not critical, are very critical. If it crystallizes, it's not good. It will be very brittle. So we see some chances and challenges of the bulk metallic glasses. They have very special properties, the very high elasticity. Thermoplastic forming was mentioned by Chris Corti as well. I will not go into depth in this. It's a special process. But on the other hand, there are some challenges, the very, very narrow composition ranges, the risk of embrittling if they're crystallizing, and of course the high cooling rate to reach the amorphous structure. And of course this material is highly experimental. There are only very few companies that are nowadays producing such material. So in this work we want to establish a processing route for these platinum-based bulk metallic glasses, and we want to demonstrate the feasibility under semi-industrial conditions by working with conventional materials that you know from your practice. So let's have a look at the platinum-based alloys we worked with. We were focusing on platinum-based bulk metallic glasses that are based on platinum phosphorus alloys. And this is a phase diagram of platinum and phosphorus. And I told you about the dramatic reduction of the liquidus temperature, which this line here is the liquidus line. And there is this eutectic composition, and the red area marks the interesting composition range of these alloys. Now this is in atomic percent, 20 to 25 or 18 to 25 atomic percent. And because phosphorus is much lighter than platinum, it's only about 2 to 5 or 6 mass percent of platinum that we are needing. There are two alloys that are studied better, and this is one alloy with 850 platinum, but it's nickel-free. That's important. And there is a 950 platinum alloy, but this shows a very low critical thickness. So therefore, we were studying two alloys. I call it alloy A and B. Alloy A is the alloy with 85 mass percent of platinum. It contains copper and around 2% of phosphorus. And it has a liquidus temperature quite low, below 600 degrees, extremely high hardness, and it has a critical thickness of 7 millimeters. So this means this is the maximum thickness that you can, where you can cast the alloy under ideal cooling conditions. So 7 millimeters is a lot for most, or enough for most jewelry objects if they're made by casting. And the density is, of course, much lower than conventional platinum, which has it's only about 15 grams per cubic centimeter. The second alloy has better glass forming ability. It has around 74 mass percent. You can also have it with 75. It contains also copper, and it contains 5% nickel and much more phosphorus. The other properties are quite similar, but the critical thickness is much higher. But of course, the nickel-free alloy would be much more interesting for jewelry application. There is these alloys were developed nearly 20 years ago by Schröers, and some of them are commercially available in Germany by a small company. So when we do alloy preparation, and we have to work with phosphorus, so that's a bit tricky, because phosphorus is highly reactive, especially if it forms white phosphorus. White phosphorus is highly toxic, and it must be avoided that white phosphorus is forming. Therefore, when you cannot simply put it into an open graphite crucible and melt it, because all the phosphorus will evaporate, will transform into white phosphorus, and so you have to be careful what you're doing. So don't repeat these experiments in your lab at home, and better ask for some assistance by someone who worked with these alloys already. What is also important, I mentioned impurities, so you can work with high purity raw material, no problem usually with precious metals, but often in laboratory or in scientific literature it's described that you need to flux these alloys. So fluxing means you put the alloy, the cast part, and cover it with boron oxide. Then you melt the boron oxide and you boil it at 1200 degrees for 16 hours. So quite a long and time-consuming and energy-consuming process. And of course, working with boron oxide is also not nice. It's also not very healthy. And we wanted to avoid this process because we think it's not practical if someone wants to produce these alloys. So therefore, we started melting in a conventional induction heated casting machine. We used high purity chemical elements. We apply them in a special way to avoid the sublimation of the phosphorus and to allow the alloying of this. And we try this first with small batches of a few grams, and then later on increased it up to 200 grams. We end up with a small pre-alloyed ingot. This ingot is still chemical inhomogeneous, so we cut the discs on either side and measure the phosphorus content, and it was not homogeneous. And because the phosphorus content is so decisive, we need to remelt the material in a second try. But it's quite convenient to alloy the material this way in a closed machine. Then for casting trials, we prepared some CAD files. We 3D printed the objects, and then we did the conventional investment process. We put some thermocouples inside the flask to monitor the temperature, the heat up of the flask, because we have to have a quite high cooling rate. And then we did some instrumented casting trials. We see the flask on the rotating arm of a centrifugal casting machine with the thermocouple wires going to a data logger, which is mounted on the arm. So during spinning, it can record the temperature profiles in the flask. So this is how we arranged all the thermocouples to with a defined distance from the wax part to determine the cooling rate in our tree. And we also monitored the temperature of the melt with a thermal imaging camera. You see the heating range. We have different temperatures plotted here. The blue line is the crucible temperature, the red curve is the maximum temperature, and the pink curve is the average temperature in of the melt. So we go around to 1000 degrees, then you see nothing happens, normal cooling, and then we have a certain undercooling, and then the crystallization occurs during cooling. And then when we heat the material again, we see the melting occurs. This is the conventional heating cooling cycle, and this demonstrates that the alloy has reached the right composition because the temperature is in the right range for casting. Then after the second heating, we switch the induction off, and then we cast at, in this case, at around 1000 degrees. We did 2 casting trials. I already told you about the centrifugal casting, and we also did tilt casting trials. Why did we do so? Because you have to prevent the crystallization. There are impurities, there is the high cooling rate, but there is another factor, which is the so-called shearing of the melt. When you cast the melt in centrifugal casting, you have a high shearing rate, and this shearing rate, it's plotted in red. This is the shearing rate during filling. You see that it's quite high during centrifugal casting and quite low during tilt casting. And the high shearing promotes the crystallization. So therefore, we first thought, well, we want to do it in tilt casting, but in the end, it was working also in centrifugal casting. In gold, this was our experience from the gold alloys. In gold, this was critical, but it's not critical for platinum alloys. Now this is a video, so could you please play the video? So you see the melt coming up and shooting into the mold. It's done very quick. And we saw, if you look the time, maybe you can play it again. If you look at the time here in seconds, you see form filling is really fast. And then it takes around 2 seconds to reach temperatures where the material solidifies or becomes amorphous. We did the same. This is the measurement of the temperatures. We had the simulation, which is the solid lines, and there is no. These are the dotted lines are the simulations, and the solid lines, the thicker lines, are the measurements. And we see that there is a quite good agreement between the calculation and the simulation. You see the thermocouples after the casting sticking to the parts, and we obtained a defect-free casting. Then we tried a small tree with small grids and some rings. We did some metallography. We found that there is a porosity in some parts, very small scattered porosity, but no major porosity, and no severe shrinkage. This poor surface here is from our simple 3D printer. We used an FDM printer in that case. So that was quite promising. So then we did a gravity pouring simulation. So could you also please play this video? We see the melt is pouring. And filling takes longer, and you see all the gas bubbles coming up, and it takes about 1.1 seconds until the melt becomes maybe you can play it again, until the melt becomes stable. Okay. Then the same result for this tree. We also see a quite good agreement between the thermocouples and the simulation. Now, this video shows the work in the laboratory. Could you please start? So this is a view to our laboratory. My colleagues, Eike and Lisa, who were doing a casting trial in the centrifugal casting machine. And so there are some thermocouples on it. And then it was dewested in water. And it was a quite filigree ring that we cast this time. It was a better quality of a 3D printed part that made on a Formlab machine. And here you see the part and the resin part and the cast part. And we really got very good form filling and very filigree items that were reproduced very well. The surface is very smooth. This material casts really very well. But now you should set a stone here. And I said settings, the material is very elastic, but not plastically deformable. So a conventional stone setting like this is not possible. We knew this before, but we wanted to test this for the filigree items. So therefore, we had to think about a stone setting. And Eike is, as I said, is a master's goldsmith, and he had a great idea. He wanted to use the elastic properties by mounting a spring-loaded stone. So this is a cast ring, and yeah, the edges are, you can use them as springs, but actually these two sides of the ring were bent over each other to mount the stone. So in the before casting, the right side was the left side and vice versa. So you had to bend the rings, the ends over each other, and something you cannot do with a conventional material. You would just bend the ring, but because the material is so springy, it's working really well to fix the stone like this. If you look at the surface of the ring, you see the 3D printed and the cast surface, and you get a perfect representation of the surface. So the form filling ability is really very good. Then we tried another example. This was a small sphere. It has maybe 10-15 millimeters in diameter. You see the 3D printed parts. It has a mesh structure on the surface, and we could cast it without problems. It was filling very well. This is the cast part. You see, again, the surface already looking very good. And this is after finishing. And this part was indeed amorphous. We proved this by X-ray diffraction. So if the X-ray diffraction pattern of a crystalline material usually shows sharp peaks. If these sharp peaks are missing, this is an indication of the amorphous state. And this is the case here. There is no sharp peak here. There's this broad peak. So that was a nice example. And this video shows the elasticity. So you see this ring is drawn, and maybe you play it again. You see it's deforming elastically to a really high extent, and without being plastically deformed. So that's really fascinating, again. And then we had this little ball, and we started playing with it. And you can throw it on the ground, and Lisa is throwing it on the ground in this video. So could you please start? So it's hard to see. You see how it's bouncing up, and it's really bouncing like a rubber ball. So it was great fun to play with it. We played with it until it broke. But it's really fascinating. So it's you throw it on the ground, of course not heavily, but it bounces back, and you can catch it at the same height. So that's really fascinating. And so what is going on? We recognize that we need to have more fundamental studies to better understand the alloy properties. So we have to study this phase diagram in more detail. The original phase diagram is nearly 100 years old, and so after over 90 years it deserves some attention to be studied again. And we also made a powder of this alloy. So we used an atomizer, plasma atomization, ultrasonic assisted plasma atomization to atomize this bulk metallic glass. You get perfect spheres, very nice powder. And we also used laser tracks on amorphous plates, on crystalline plates, and made laser tracks on the surface, and we recognized that the material was becoming amorphous due to the fast heating. So this was first work for maybe another interesting study about the additive manufacturing of such bulk metallic glasses based on platinum. Yeah, so this leads me to the summary. Bulk metallic glasses have fascinating properties. They are very highly elastic. They have high strength and hardness, very low melting temperature, which makes them perfect for casting. If you reach the sufficient cooling rate, which we did by investment casting with conventional investments. There are different alloy compositions that behave different. The best glass former is the one with around 750 platinum. The higher the platinum content, the lower the glass forming ability is. It can, after casting, it can be finished in standard techniques and to produce really high quality surfaces. So with this, I want to thank my project partners from University of Saarland in Germany, my colleagues at FEM. We have an industrial users committee that was accompanying and supporting this work. I would also like to thank them, and of course for the financial support by the German government. And I thank Legor Group for inviting me and having the opportunity to giving this talk here, and thank you very much for your attention.
Grazie mille Ulrich, grazie per la presentazione.
Many thanks, Ulrich. So we are pretty late with respect to the agenda. If you want, we can go. You can go for a coffee, but we will go on with the program. So now we have Owen Houghton, University of Cambridge, who will speak about amorphous metallic glasses, sharing his experience. Owen Houghton is a PhD student in goldsmithing at the University of Cambridge, UK, with the research subject on amorphous precious metal alloys. He holds a Master of Science in Material Sciences and a Master of Art in Natural Sciences from the same university. Now, with reference to the presentation, amorphous metallic glasses and precious metals are a relatively young class of materials that are used in jewelry is of particular interest because their characteristics allow for the production of wear-resistant jewelry that can be processed with systems similar to those of polymeric materials. Now we will discuss the state of progress in this area and short and long-term prospects for their use in the jewelry sector.
Thank you very much. So, good afternoon, everyone. My name is Owen Horton, and today I'll be presenting the second of two presentations on bulk metallic glasses and precious metals. So in this presentation, I hope to briefly discuss the structure and properties of metallic glasses, their advantages as jewelry materials, and the current state of the art and the challenges facing their widespread use. There we go. So before we start, if you understood as much as Andrea's presentation as I did, you'll be pleased for this bit. I'm a PhD student at the University of Cambridge, where I also completed my undergraduate studies in natural sciences and then a master's in material science. My PhD focuses on precious metal-based bulk metallic glasses, and specifically the atomic and kinetic behavior of metallic glasses and developing new 18-karat gold metallic glass-forming alloys. This is under the supervision of Professor Lindsay Greer, who's seen at the bottom of the stairs, and I'm supported primarily by the Worshipful Company of Goldsmiths and the European Research Council. So we will first discuss the nature of bulk metallic glasses, cutting out a little bit courtesy of Ulrich's kind introduction, and how they differ from crystalline materials. We will then discuss how metallic glasses can be formed. After this, we will discuss the advantages and desirable properties of bulk metallic glasses as jewelry materials and how they have the potential to deliver new opportunities. And lastly, we will discuss some of the current limitations and challenges facing bulk metallic glasses as jewelry materials and what recent work has been done and what work is currently underway. So, as you all know by now, metallic alloys are typically crystalline. That is that all the atoms are arranged periodically throughout space, and we have something called long-range order. By contrast, a glass can basically be described as a hardened, cooled liquid. It has the structure of a liquid, but the resistance to deformation of a solid. It therefore differs substantially from conventional crystalline jewelry alloys. So while it's tempting to draw comparisons in metallic glasses to polymers and oxide glasses, such as window glass and silica, we need to be careful because in those structures we have chains of atoms which are entangled together, which is not the case in metallic glasses. It's the atoms that are randomly distributed. So when we form a metallic glass, we take it from the liquid state and we want to cool it very quickly to avoid crystallization. And so we can measure these properties using what's called an isothermal time-temperature transformation curve, which I've measured here for one of the gold-based glasses. So you'll see two red lines here. On the second one, labeled 2, or on this side, labeled 2, we have a critical cooling. We have a cooling rate that will entirely form a glass. The second line, labeled 1, is for a critical cooling rate to avoid crystallization. And that intersects this black C curve here, which is the measure of the time for crystallization to occur as a function of temperature. And if we do this and we cool fastly enough, we will reach this glass transition temperature. And that's the temperature at which the atoms are effectively frozen into the glass and they are thermally arrested. So our aim from the previous slide is to push this C-curve as far to the right as possible. And we can do this by adopting several strategies in choosing our alloy. So first of all, as Ulrich was saying, we typically choose these eutectic compositions, so where the red line intersects the blue line. And that means that our liquid is as stable relative to the crystal for as long as possible. And so the temperature gap between here and where the glass transition would be is as small as possible. Secondly, we will design our alloys with 4 or more elements. This does several things. It ensures dense packing within our liquid, so the atoms can't move around as quickly. But it also means that when it does try to crystallize, there will be many phases trying to crystallize at once. And so it's a bit of a mad rush, and ultimately none will crystallize. Those atoms we choose quite carefully. So our elements are chosen for varying atomic sizes. This helps promote the dense packing. And we also want to make sure that chemically they all like each other the same amount so that we don't get any phase separation. So that's a very quick introduction to the principles of how we form metallic glasses. We will now go into why they are useful as jewellery materials. And metallic glasses have been used and proposed for various applications, ranging from biomedical implants and now space applications. But they're probably most famous for their use in electrical transformers, where they have very low resistance, and so there's minimal heat losses involved. So since the advent of platinum and gold-based glasses, which was by Boonrat Lowong-Ratana, and as Ulrich explained, those glasses have sufficient hallmarking standards for the jewellery trade. So as you can see, there is a wide variety in glass forming ability. So as Ulrich was saying, we have this critical casting diameter, which scales with cooling rates. And we call any glass a bulk metallic glass if it can be cast in sections thicker than 1 millimeter. So here we've got all various types of metallic glasses. So as you can see, palladium's nice and high at the top, and gold is more towards the bottom. It's worth noting that there are very few silver glass forming alloys, and none of them are near the sterling silver fineness regulations. Yeah, we've got our palladium glasses up here, and then we've also got these zirconium ones. So for some of you familiar with the watch trade, these zirconium-based metallic glasses have already been used under the trade name liquid metal and are often used in bezels of certain watches. So one of the main advantages of BMGs is their hardness. So here we've got a chart of different metals and the crystalline alloy and a BMG of comparable fineness. And as you'll see, the hardness is typically at least twice as high. And this is due to their atomic structure. So whereas in a crystal we have layers of atoms that can slide easily over one another, they don't exist in the glass. And so glasses actually deformed by a mechanism of shear band, which I won't go into. But ultimately it means we have very high elastic strains under large loads. And so we don't see macroscopic ductility in the same amount, but we do have much higher hardness. Oh. So you've seen this video already, but it's worth demonstrating again because it's quite incredible, really. So I thank Ulrich for letting me use it. And as you'll see, the elastic behavior is quite incredible, and it actually sounds a lot like a rubber ball, simply because of that elastic phenomena. And so failure here will occur by the shear bands, but that occurs at much higher strains, allowing the ball to bounce as much as it does. And again, we get new design opportunities courtesy of these metallic glasses because of their high elastic properties and the fact that because they're so hard, the gems won't deform the metallic glass. So in terms of processing, Ulrich talked in great detail about investment casting, but there's also this advantage that because metallic glasses are so much like polymers, there's a process very analogous to plastic injection molding. And there's several companies that are able to do this. And the key advantage is time. So as you all know from Ulrich's talk, we have minimal shrinkage on casting, and we have very good surface finishes. And so we can actually cast rings in matters of seconds, opposed to the extremely long time, relatively long time for investment casting. Next slide. So we'll now go on to the current limitations and progresses on the issues. So as we've already mentioned, we need extremely high cooling rates to form metallic glasses. And not only does this create issues with actually forming thick sections and forming glasses in the first place, it will also create many issues with form filling, and so we have to be careful about the design of our castings. The other issue is generally regarded about hallmarking standards or stamping regulations. So this is a bit of an expansion on the graph that Ulrich showed. It's to include the platinum and palladium and the gold systems. So for all commercially available systems at the moment, gold is preferable, largely because there's a much larger composition space to work within, thanks to the 18-karat hallmarking standard. But for our platinum and palladium systems, we're right at the cusp of this 950 hallmarking fineness. And so the large issue comes into considering that given that we need about 15 atomic percent metalloid or other additions to form a glass, we can only be using a certain range of light elements. So I show a table, which is perhaps some of the figures you may have already seen, but you'll see that as we go to our higher finenesses in our platinum and palladium systems, we typically have an issue with critical casting diameters dropping off markedly. And these ultimately mean that they're of little commercial use at the moment. And we'll also see a drop in this thermoplastic formability, characterized by this S value here, and that's of importance for the injection molding analogs. So we now move on to the issue that Ulrich didn't concern as much, and that's in these white gold alloys. So that the alloys are white in general because of their high silicon content, but unfortunately these alloys tarnish abnormally fast. So this is a sample, a white gold ring that's just been worn for 52 days, and as you can see, there's a dramatic tarnishing phenomena that's going on. So extensive work has been used to characterize these systems in general, and the tarnishing mechanism is widely understood. So when we cast these alloys in air, in general, we will get a crystalline silica layer that forms on the top, and that is in fact passivating and stops this tarnishing occur. But with polishing and general wear, that surface layer gets removed, and then we see this tarnishing phenomena starting to occur. So the first behavior to occur is this outward diffusion of copper from within the glass, which is actually able to oxidize the silicon that wouldn't occur otherwise at room temperature. And ultimately, that leads to these rather well, they're not dendrites, but because they're not crystalline, we use the term dense branching morphology. But in essence, we have this inward oxidation of silicon and the outward depletion of copper, which leads to this reddish-brown appearance on the surface. So what might we do to solve this? There's been very, very, very many attempts to try this. So at first, people started playing around with the copper-silicon ratio and removing elements such as palladium. But ultimately, that tended to lead to a loss in glass-forming ability, and so we can cast in even thinner sections than we could already. People have tried to add other elements in order to try and stop the tarnishing behavior. And in general, we see some improvement in tarnishing behavior. So this is the tarnishing depth of that corrosion scale that I schematically show here. And you'll see some improvement, but ultimately also a drop in our critical casting thickness. And so perhaps the best achievement to date is by Oliver Gross and Nico Neuber, and they were able to take the Schroer's alloy shown up here and reduce it down to, sorry, that's not the Schroer's alloy, that's their intermediate alloy, and then ultimately they were able to get down to tarnished scales of this value, which you can see are much whiter than they would be otherwise. But unfortunately, they had to use an effect called ion implantation, and that requires a gallium ion beam and is of limited industrial use, largely because wear will remove that surface layer, but also it's very difficult to do that on non-flat surfaces. So during the course of my PhD, we've taken a slightly different approach. So rather than working on high glass-forming alloys and improving the tarnish resistance, we went right back to the start and considered all the elements in the periodic table and which ones would be glass-forming using the principles that I outlined before. And we identified good glass-forming systems and then tried to improve the glass-forming ability from there onwards. So as you can see, this is using what we call a focused ion beam scanning electron microscope. So for those of you that are more interested in the technical side of things, the magnification is 50,000 times, and the working distance is 5.1 millimeters for both. So they're at the same scale. And so as you can see in the Schroer's alloy, we have a tarnishing depth of about 400 nanometers. And in our newly developed alloys, we're put down to about 80 nanometers. So we're largely at a close to a commercially viable alloy. Obviously, that's only one half of the story. We've got to improve the glass forming ability as well. So these are X-ray diffraction measurements. So these are these thin cast ribbons that we start at, and these are about 100 microns in thickness, 100 micrometers. And then we try to develop even thicker castings. So as you will see in the samples at 5 and 6 millimeters, we start to see these crystalline peaks, and that's indicative of some crystallization occurring. We think they were to do with palladium silicides, and so there is room for further optimization. And so hopefully we'll be able to pair this with this, but for very thick sections. Other work we're doing is kindly in partnership with Ulrich and his colleagues at FEM, and we're generally starting to look at the wear behavior. So it's generally understood that hardness would scale, wear resistance would scale with hardness. That's known as Archer's law. But in a recent publication by Ulrich and Lisa at FEM, they found that that's not so much the case, and so BMGs might not perform as well as first thought. And so there's some quite fundamental work to do to understand that. So using the extensive testing and characterization facilities available at both Cambridge and FEM, we're hoping to understand this phenomena to make more industrially viable alloys. So in conclusion, we've come quite a long way in metallic glasses. So we started off in the gold system in the 1960s. That was over at Caltech. And in the 60 years since, we're almost at the point of hallmark-compliant bulk metallic glasses. And so going forward, we've got these harder and hopefully more scratch-resistant alloys in many cases, but in not all. There are new design opportunities, and there's also the case for faster, higher definition production that could rival technologies such as MIMS. Unfortunately, there's still challenges to go, and that's largely about this developing these tarnish-resistant compositions, achieving high glass forming ability with high fineness, and also understanding the wear phenomena. So I'd like to thank you all for listening. Thank you to Andrea and Legor for the invite, and also thank you to Ulrich and Lisa for their kind use of their images. And lastly, but not least, to my funders, the worshipful company of Goldsmiths and the European Research Council. So thank you very much, and go and enjoy a coffee. Thank you.
Ok, siamo quindi giunti all'ultima sezione del nostro evento di oggi. Cominciamo quindi con la parte relativa al Responsible Jewelry Council. Dovremmo avere in collegamento le presentatrici di questo intervento. Intervento dal titolo RJC e la trasformazione digitale nelle certificazioni, a firma di Sonne Douden e Andrea Congianu Davidou. Hello there, can you hear us? Hi there,
Hello. Hi there. This is the last leg of the conference. We have Sonne Douden. She has been working for more than 19 years on the validation of processes and systems to improve growth and efficiency. She's got a bachelor's degree in business information systems. Thanks to her experience in digital transformation, she supports companies in translating the business strategy into operation. Andrea Congianu Davidou, General Manager for Standards, Assurance and Certification at the Responsible Jewelry Council. She has been working for 15 years to improve the ethical conformity and improve quality. She's got a master in human rights and human values and a master in intercultural cooperation in contemporary business environment. They will speak about modernization and digital transformation of thinking and systems and participating in the global industrial sector and the positive impact in the supply chain. They will speak about the transformation with the objective to inspire and reassure those who are going through these changes.
As soon as you like, and thank you.
Thank you. Hello, everyone. Thank you for the invitation. It is a pleasure to be able to participate today. My name is Andreea Cojanu Davidoiu, and as per the introduction, I am General Manager for Standards, Assurance and Certification with the Responsible Jewelry Council. I have been with the Council for a little over 2 years, and I'm joined here today by my colleague, Sanette.
Thank you, Andrea, and hello, everyone. Thank you for your warm welcome. My name is Sonnet Dowden. As per the introduction, I am the Senior Manager of Digital Projects of RJC. I have been with the RJC for just over 3 years now, and we're here to share with you how we've used our digital transformation journey so far to deliver efficiency in our certification system. Thank you. Just to give an outline of how the presentation will be sort of shared between myself and Andrea. Andrea will be giving an overview of who the RJC are and what we do, some sort of overview on our membership. I will then share some background on our transformation journey from a technical and project management perspective. And then I'll hand back over to Andrea, who will give a case study of the RJC and from the user perspective of how our digital transformation journey so far has improved processes in the certification system. Then I will share very brief sort of key learnings that we've had so far on our journey and what's next for the RJC. So I'll just hand over to Andrea, who will kickstart with an overview of who we are and what we do. Thank you.
Thank you, Sanette. First of all, the Responsible Jewelry Council is a membership organization, and we are also the scheme owner, the standard owner for the Jewelry Industry Sustainability Standard Code of Practices. We believe that more sustainable, responsible supply chains are achievable by implementing our Code of Practices. The standard includes strict environmental, human rights, and supply chain due diligence. We also believe that by transforming the world's jewelry supply chains to be responsible and sustainable, the RJC can help to create beautiful things in a beautiful way. And therefore, in doing so, we build and deepen trust in the global jewelry industry and its future. So people continue to hold jewelry close to their hearts for centuries to come. This is, as such, our promise to the customer, and this is our mission at the core of what we do. The RJC was founded in 2005 by 14 companies to lead change with an ambition agenda, to build trust and confidence with consumers and within the supply chain all the way from mining to retail. Today, of course, we continue to support our members. We continue to develop transformative partnerships to move our industry beyond compliance and to deliver meaningful and measurable impact on a global scale. When it comes to our membership base, we have now reached over 1,680 members all over the world, globally. Just to give you an idea, we have 76 countries where there are RJC COP certified facilities, and there are 16 countries where we have RJC COC certified facilities. When it comes to our standards, we have two. One is called Code of Practices, one is called Chain of Custody. The Code of Practices is mandatory for our members. They join and then they have 2 years to become certified against the Code of Practices. This code is focused on management practices. This includes labor, human rights, supply chain due diligence, health and safety, gender equality, non-discrimination, product integrity, and the environment. It's important also to outline that it is aligned with the UN guiding principles of business and human rights and the OECD due diligence. The chain of custody, our second standard, is voluntary for certified members against the Code of Practices. So members can only look for certification against the chain of custody after they have achieved certification against the Code of Practices. This code, as per its name, It's focused on material and the flow of gold, silver, and platinum metals through the supply chain. And it does include conflict-sensitive sourcing. And now I'm handing back to Sunette to take you through our transformation journey. Thank you.
Thanks, Andrea. So as sustainability continues to grow in importance for consumers and organizations worldwide, demand for RJC membership has remained high. In 2020, the pandemic accelerated our requirement to develop new and efficient ways of working and serving our members and stakeholders. In fact, demand for RJC membership increased in 2020 and 2021. RJC's board and executives understood the value and importance of a sound digital strategy and set this as a strategic deliverable with significant investment in modernizing our systems and processes. So in addition to meeting the challenge of growth and finding new ways of working in this new norm that we all found ourselves in, we also wanted to improve our member and stakeholder experience. As Andrea just mentioned, with over 1,680 members and counting across the globe, across sort of 76 countries and multiple time zones, we wanted to create digital tools to enable members to access resources and manage their membership and certification wherever they were located. We also wanted to obviously improve efficiency in our certification system to keep abreast of changes in the regulatory landscape, to demonstrate impacts, the impacts of our standards through quantifiable and data-driven insights, and to gain an end-to-end view, a unified view of our members throughout their certification journey. We also wanted to maximize our operational efficiency and sustainability within our teams to better serve our members. So these were some of the key objectives driving our transformation journey. Start where you are, use what you have, and do what you can. We think that this quote by Arthur Ashe fits our case study perfectly. If you read or listen to anything on the topic of digital transformation, the words journey and marathon will come up at some point. For us at the RJC, our journey started by migrating our legacy systems to the cloud, decommissioning our old IT infrastructure, and introducing new tools and ways of working. We collaborated with our team on the digital strategy to foster ownership. Each department takes lead in shaping and redesigning their processes. They are an integral part of all the requirements gathering workshops, sort of all the process mappings that goes on before a system is developed and deployed. It was very important to identify and engage the right digital partners to embark on this journey. Next, we identified scalable and secure platforms for our back office and online systems. Then came the unavoidable task of migrating and cleansing data from multiple siloed systems. So, and also significant time was spent mapping processes and scoping for this project. Thank you. Next slide. What we've learned is that this is an iterative synergy of people, process, and technology. So these are some of the approaches that have worked best for us so far. First, to recognize and normalize that it's a journey of continuous improvement. To define which methodology best suits our organization. To define and agree what success looks like at each phase. To keep project teams engaged throughout, especially as they carry out their day-to-day duties. And also the importance of managing expectations, being prepared to communicate budgetary and time constraints. Change management is also key to ensure smooth transition whilst minimizing risks and disruptions. Thank you. So in terms of our roadmap so far, we started this journey in 2020 by the migration, as I mentioned. In 2021, we launched our newly designed CRM system and started the first phase of our certification automations. A lot of these processes were manual up until then and very time consuming. We also launched the first phase of our member portal. For the very first time, our members were able to sort of log in, gain access to the information that the RJC held on them, make changes, make online payments, and so on. Andrea will share more about that in the user case study. In 2022, we launched the second phase of our automations on our CRM system and launched our digitized application system. So now applicants were able to complete an enhanced due diligence application form digitally and submit supporting documentations. We also strengthened cohesion of data across our departments, and this is something that we will continue to do, and one of the benefits that we'll continue to see as digitization continues. In 2023, I'll talk a little bit more about this in terms of what's next, but we're working on launching an enhanced due diligence system for our existing membership, and also to develop the first phase of our audit portal. And as always, at each phase, we are continuing to add more automations as we go along. Thank you. So now over to you, Andrea, for the case study.
Thank you, Sonette. I will walk you through the perspective, the user experience of the certification process. All of these steps and transformations that Sonette has implemented have obviously been used, reused, and reviewed, and they now make up our certification process. Just to give you a bit of an overview of what the RJC certification process is outside of digital. So first of all, step one is the self-assessment of the member, which is a questionnaire where the member will answer questions and self-assess themselves against the code of practices. They need to do that before they embark on the audit journey, and they need to provide that to their auditor. It also helps them understand where they are compared to the code of practices and what they need to address before they actually go for the audit. Second step is the audit, which is done by a third-party, independent RJC-approved audit firm selected by the RJC member. It's a relationship between the member, the RJC member, and the audit firm. Afterwards, once the audit is completed, the auditor will complete the report, and the report will be submitted to the RJC and reviewed by the RJC certification department. At the auditor's recommendation, the certification decision is the next step, followed by the RJC issuing the certificate. Next step, the last one, is review and recertification. This means that the audit cycle, we have an audit cycle of 3 years. We can have an audit cycle of 1 year, but the generic one is of 3 years. Members can have a midterm review or a surveillance audit. And then after that, they will resume the steps and embark again on the next auditing cycle, going back to the self-assessment audit and so on. Moving on to the digital challenge and leaving the operational side aside, both the RJC certification and the underpinning assurance processes, they integrate analytics and data insights to understand how the audit firms and the auditors are performing, where the RJC members are on their certification journey, and of course, how members are performing against the RJC standards. As you can imagine, the data volume is quite significant, and as Sonette mentioned, at times manually introduced onto the system. The RJC certificates are also issued based on audit and member data in a bespoke design. We wanted to give you a bit of an idea of the volume that we have, and you can see that for 2022, we've received 807 audit reports, and we were able to issue 828 certificates against each report reviewed and against each certificate issue, there's a significant amount of work that comes behind, and there's a significant amount of data. And of course, that was our digital challenge, to be able to manage that and still deliver the service to our members. Following our digital transformation, we've had a few digital wins that we would like to share with you. So for example, now relevant data is captured, is accessible, controlled, and monitored. We have charts and dashboards based on live data. This in turn has helped improve the trend analysis, the reporting, and the transparency, all the way, not just internal transparency, but also public transparency within our 2022 report that was issued last year. Of course, this also led to stronger departmental communication, collaboration, and transparency. We were able to implement automated email reminders to the RGC members on audit deadlines, which means that the members will receive an email 6 months, 12 months before their recertification deadlines, and then again 6 months before their recertification deadline, to remind them to start preparing for the audit, to start engaging with their chosen audit firm. We can track our member certification journey as well. And of course, via the member portal that Sanette mentioned, the members can access and update their own information. And they can also pay for their membership renewal via the same member portal. Any applicants can apply online and submit their documentation together with their attachments. And finally, maybe one of the most important digital wins for us is the fact that we can generate the RJC certificate with a click of a button now. And it's literally as easy as that. All of these digital wins have enabled us to improve the service, to provide a better and faster service to our members, and we continue to be committed to improve and to go on this transformative journey. And back to you, Sanette. Thank you.
Thank you. So just to share some key learnings that we've had so far. Technology isn't a silver bullet. It doesn't fix everything straight away. Be prepared for some discomfort as processes are redesigned. Changes is, it's uncomfortable, but it's exciting. Thank you. The next one, business leaders need to show up. It's so important that we have the backing and the sort of support of the business leaders. It's strategy, not the technology, that dictates digital transformation. Culture eats strategy for breakfast. I like this quote by Peter Drucker. A clear digital strategy isn't enough if you don't have the input and the buy-in from users and key stakeholders. It's important to bring them along on that journey. The process of involving the certification and assurance and membership departments as integral parts of the designing of the new process and the new systems is absolutely critical. And also to identify who your champions are in the team and engage them. Tie results to something measurable. Again, probably tied to the first point. Just having additional automations and all the bells and whistles doesn't actually mean more benefits. So identifying what success actually looks like and what will make the biggest impact is key, along with your stakeholders. And the next one, it's a marathon, it's not a sprint. There is a learning curve that we all have to go through in designing these systems. It's an iterative process of sort of, designing, planning, implementing, sort of learning sort of backups and feedbacks, and then going back into the loop and improving as you go along. So those were some of the key learnings that we've had so far. In terms of what's next in 2023 and beyond, we will continue to develop systems to improve our member experience and also to improve our insights on the impacts that our standards are having across the industry. We'll start work on the development of our auditor portal to further automate some of our certification processes and launch the enhanced due diligence system via our member portal for our existing members. This is particularly important in terms of the changing regulatory landscape in our industry, and continued development of various digital tools to enable members throughout the supply chain to remain certified, engaged, and committed to the RJC. And that's it, I think, from us. Andrea, I don't know if there's anything else you wanted to add on this. Thank you very much for having us share some of our insights with you. Andrea?
Thank you, Sanette. I also wanted to share Legor for the invitation today and for your time and attention. And I hope we've shared a bit of light into what the RJC does. And if you're curious to find out more about us, please don't hesitate to get in touch. We're always there, ready to answer any questions applicants or members have. Thank you.
Grazie mille a Sonia e Andrea di RJC.
Many thanks to Sonia and Andrea of AJC. And now we come to the last two presentations of today, which are related to the issue of benefit corporation and B Corp. The first presentation will be by Matteo Meneghini, Scientific Director of Green Media Lab and CEO of Impact Manager of Colonization. He's an environmental economist who has focused his career on developing impact synergies between man-made elements and natural ecosystems. So what does it mean to be a B Corp? And the presentation starts from the state of the art of the ecosystem and the impacts on human society, the role of corporations, and then describes the emergence of B Corps and benefit corporations, going into details as to how to measure the impact of one's own company and how a B Corp journey is structured. Well, good afternoon. First of all, many thanks to Legor. Today is a very important day for me because in this sector we're starting to speak about sustainability. Now, I would like to lead you to understand what it means to be a B Corp. That is a company which solves problems, creates added value, and does so by creating profits. So we're not speaking about not-for-profit companies. We're speaking about companies which solve problems. Well, I love this work. I like this job. So what does it mean to be a B Corp? So Andrea already introduced me, so I will not repeat what he said. Well, we have a big problem. We have a huge problem. This one is a chart of the concentration of CO2 in the atmosphere, BPM, parts per million. Now, for 800,000 years, when we can trace the concentration of CO2, we had 180 BPM. Now it's 409 BPM. Well, there was the third great extinction in the history where 97% of the life on Earth disappeared. Why so? Because CO2 got to 800 BPM. So it was a process of acidification. Life was not possible on our planet. Now, as you can see in this slide, there is a symptotic curve. And if you look at the time, here we use the time in 800,000 years. Well, this curve starts from 100 years ago. So we doubled the CO2 in 100 years. If we continue in this way, we will have complete extinction of our species, but also of all other species. So we should really ask ourselves, are we really sure that we are the most intelligent species in this planet? So we speak a lot about climate changes, but nobody has really understood what that means. So we doubled CO2. We have climate changes. We increased temperature only by 1.2, and that led to desertifications. We no longer have snow in the mountains, and this will cause migration flows. We complain about tens of thousands of people who cross the Mediterranean Sea. Well, the prospect is millions and millions of people that will have to move from Africa, because where they live, it will no longer possible to live or grow something. It is unavoidable, inescapable, and this has a huge cost. It's 3,000 billions per year up to 2060. That means $3 trillion, million dollars. What about our public debt? 2,400 billions. Well, think that every year the world economy will miss and lose $3,000 million. And this will lead to an upheaval, to a revolution in our habits. Companies will no longer be able to go on. So let's start to raise questions. So climate change is a very fashionable word, but nobody speaks about biodiversity loss, social problems. Well, I went to Los Angeles at Beverly Hills, beautiful places, and in front of those villas, there are thousands and thousands of people who have no home, homeless people. So social inequalities are increasing a lot. So imagine what will happen when the nations, when the populations will really clash in order to have access to resources. So what I'm telling you is not science fiction, it is reality, and it's taking place very fast. We have a very short historical prospect. This change is a change that in the next 15, 20 years will be inescapable and will completely change your life, the life of our children and our grandchildren. No. We cannot wait for the governments to produce laws to regulate this. There is no time. I like a notion, a northern notion, where the company exists to resolve problems. A company exists within a social fabric in order to create value, generate value, and solve the problems of that society. So it is the task of companies to tackle those problems, because companies have the skills to do this transition, and companies and entrepreneurs can decide, can have a long-term vision. Now, what is the problem with politics? Well, if a decision is taken which is not particularly pleasant for one's own voters, in 2 or 3 years' time, those voters will no longer vote for you, while a company can make difficult choices, and only companies can make difficult choices. Well, B Corp means benefit corporation. B Corps are the core of environmental, social, and governance. But this wording is wrong, and I will tell you why. Because it's exactly the opposite. We speak about planting trees, but it's like putting a band on a wound. You have to avoid the wound. Now, Governance, social, and environmental. This is the picture that I propose. Governance is the software which manages the behavior of your companies. A good software makes it possible to have a good corporate management, while a bad software condemns the company to failure. So the first thing that you have to do is to start from governance, and then the second thing that you have to do is to apply that governance. And then social. People are the hardware of a company. A company cannot exist without its people. People have to be involved and have to be convinced that this transition is necessary. And this makes the difference. Now, do you know that there are companies where the staff do not like their job? Well, those companies have a big problem. Well, imagine companies where the staff are passionate, where the staff are ready to do everything in order to achieve a common objective. Well, that is a company which works well. And then environment. Well, environmental sustainability is nothing but efficiency. The efficiency of reducing waste. It's a question of material flows. The environment is the one which gives us the inputs. We transform those inputs, but we don't use them well. And the environment is a perfect balance. Now, the UN has realized that, well, many of you heard about SDGs, Sustainable Development Goals. There are 17 of them. And they start from one point, that is the social aspect. And then they move to economic development, and then environment, because that is a consequence. But perhaps the most important SDG that we often forget is the number 17, which has to do with synergy, with cooperation between all the stakeholders. So this problem cannot be solved by just one country or one company. We have to collaborate. In Italy, legislation has made progress. We have the SDG paradigm, which has been interpreted by the legislation and also by a movement. The Italian legislation has created the benefit company, that is a company which is for profit, but which includes some impact objectives, which can be environmental or social in nature. And then the second company is the B Corp, that is a certification, a stamp, which is given after passing an audit by a third party. And both things go hand in hand. Now, let's start from the benefit corp. A benefit corp is a corporation, is a company which understands things and which introduces impact objectives. Let's make an example. Legor. You are going to become a benefit company, let's assume. And you work with raw materials, high-value raw materials, and your objective will be that of making the use of these raw materials more efficient and improve your supply chain, improve your ecosystem and all your stakeholders. So this is the first point. And the second point is the fact that you want your staff to be happy. You want your staff to live a dignified life. Well, I saw that because I was invited by people with whom I had already worked. And the first thing that I noted is that they smiled. And you know, a smile, the smile of people, is something which is fundamental, because you know that those people will not leave you. And remember that 51% of companies have a challenge that is finding staff and not losing them when they find them. So congratulations to Legor, because to see these two people smile, well, that is something very important. Now, what is a B Corp? Well, it is similar to a benefit company, but it is something more. A B Corp is a company which is ready to test itself, to be tested, to be analyzed, to be transparent with all the other companies. It is a company where you ask a third party, a B lab, to come over and to be tested and judged. And that judgment will be exhibited to everybody. So a B Corp is a certification, is a stamp, but what is beautiful in the B Corp is not so much the stamp. The beauty of B Corp is that it is a movement. When I meet colleagues, above all the colleague that will speak about this experience later, well, I can assure you that there is a common denominator in terms of values and intentions. And the B Corps help themselves mutually, so much so that the benefit company legally comes from a positive lobbying action made by the B Corps. So that means that there have been companies which have used their power, they put it together, and they did positive lobbying so that the law could be changed. So much is said about negative lobbying. For example, with climate changes, I invite you to go ExxonMobil in the internet, one of the most important oil companies in the world. In 1970, in a board meeting, they presented the expectations and the consequences of climate changes. What is frightening is that they really guessed it. They knew exactly. And there was a speech by the new CEO that shortly said, think if our shareholders would know that, what would they do? They would use other sources of energy, and we would collapse. And what did they do? They spoke with other companies in their field, and they did lobbying, a very effective lobbying activity, and the scientific community was not able to contrast that community of lobbyists who were very effective. So that is the power of lobbying, and the B Corp movement is the power of synergy. And then the B Corp movement realizes that we're all interdependent. Imagine a company which has suppliers, and one of its suppliers by chance fails, and the company doesn't know how to replace that supplier. So B Corps realize that their well-being, their success depends also on the others, because we're not isolated, we're not islands, we live in a society, we are connected, and that means that we have to think of ourselves, but also of the others. In Italy, we have a huge problem, which is the common goods situation. If something belongs to everybody, it belongs to nobody. So look at what happens in our country. And this is a big problem. Now, the companies can decide because they are responsible, and companies together can change things because they know that the one depends on the other. If something happens to a company, that will have repercussions also on other companies. But if a company is successful, that has a positive consequence also on other companies. So externality, it is called. Something which cannot be quantified economically, and it is something which is out of the economic standards. So we depend on the ecosystem. And then inclusion. Well, companies are interdependent, and so they do not underestimate the force and the strength of smaller companies. I myself have been helped by bigger companies. I was as lucky as to create a new company. And those who helped me, those who inspired me, is Patagonia, which is one of our customers, of our clients. And Patagonia spent money and time to help me find solutions. So the notion is that you do need to be paid sometimes, but you can help your colleagues in other companies, and that can bring you huge benefits. Well, also these figures have changed a lot. I will go fast also because we're a bit late. So the B Corp started, is a movement which started in 2005, and in 2016, 2017, there was a big acceleration. And it's something that is running and running. It's a movement which has incredible figures. Well, in Italy, up to some months ago, there were just 120 B Corps. Now there are 200 B Corps. Look at the turnover. Now there are 6,000 B Corps in the world. So, do you remember that we said we spoke about synergy, inclusion, interdependence? Well, B Corps, if they have to choose someone with which to work, they will choose other B Corps. So think that there are other 6,000 B Corps. That means that there are 5,199 potential partners. Perhaps you're not in the same industry, but these companies have experience to share with you. Now, ESGs. In order to become a B Corp, you have to undergo an assessment, which is called B Impact Assessment. Well, I have an economic background, and I can tell you that what cannot be measured does not exist. That implies that in order to become a B Corp, you have to overcome a test, a very difficult one, which covers all the aspects of corporate life. There are 5 fundamental issues: governance, workers, community, and I'm referring to all the stakeholders, from the state to the citizen, your suppliers, your customers, and then environment. You cannot be a B Corp if you don't have a holistic approach to business, because if one of these pillars is lacking, all the castle falls down. Well, now we speak a lot about outsourcing, charities, which is often used for marketing objectives. But the first thing to do is to work inside. You cannot do something without being that thing. So we spoke about governance, we spoke about a B Corp, which B Corp, a benefit corporate, have conduct codes. They are the software which implement your company. Now, 51% of companies do not find workers. But think about losing your own workers, because people are the things that are most worthy. So if you spend a lot of time to train a person and then you lose that, you miss that person, well, that's a huge problem. And perhaps you will recruit someone who doesn't have the same skills as the previous person. So you have to start from your people, from your staff. A person who is not motivated, who is not passionate, who is depressed, so much so that depression is the first disease in the world, above all in the Western world. So what do you think that a depressed person can do for your company? They will be inefficient. A depressed person will produce 1/3 of what they can produce. Well, think of a motivated person, a person who believes in what your company is doing. Well, that person will be ready to wake up at 4 in the morning to solve the problems of your company. That person is smiling, and smiling is contagious. It is something which creates synergy. So imagine that you involve your staff, and that staff is happy to work for you, and you will have more productivity, and that means more profits. So sustainability is something really tangible. Everybody thinks that it is a source of science fiction, but sustainability is real. It has to do with profits, and it starts from people. Now, how can you involve people? So first of all, you have to understand what is important for your community. You have to define that picture. You have to have values. And then in every community, there are leaders. There are people who are ready to fight. So you have to identify those people and give them the means so that they can really do something. And those people will involve their team, and the teams will help create a culture. So we always start from the culture. A company without a culture is an empty company. And then third issue, you have to devise a strategy, and you are the leader. You're not a boss, and there is a difference. If the strategy is developed together, so the leadership works with their champions, well, that strategy will be something that every person in your company will want to share. And only after that you can go out of your company and you can take your values, your way of doing things, and involve your stakeholders. So you should start from your suppliers. If your suppliers have a problem, well, that problem is also your problem. Help them improve. If they improve, they will be able perhaps to lower costs, and you will pay less, so more efficiency. And if there is a strong link between all the stakeholders throughout the supply chain, that supply chain becomes resilient, anti-fragile, Taleb would say. So something resilient is something which can be pushed without getting broken. But our world is fragile because it's a rigid world and because there is no such synergy between the various stakeholders. So some practical examples, I could speak for hours about that. So what can you do? The first is to devise policies and have a commitment. So the first phase is to have a commitment and take up responsibility and say, if those commitments are achieved, it is our merit. If they're not achieved, it is our fault. So taking up responsibility is fundamental. And then the second point is to create teams and delegate responsibility to your staff, because when you give power to those people, well, they will surprise you. They will create something unexpected, I can assure you. Well, in my working experience, I had a problem of burnout, and I was lucky because there was a colleague, a woman. I trusted her, and that person helped me get out of that difficult time. And that person now is the leader of the team that I had created. And I can assure you, well, we should never underestimate people. People have a lot to do, but simply sometimes we don't give them the possibility to give things, and then do not behave as an isolated item. The various units should share things, should speak one with the other. So contamination between different viewpoints leads to new ideas and to exchange of information. So the lack of information is a risk, a huge risk, because it happens that a person in the production unit is aware of something and the person in the marketing unit is not aware of that thing, because they do not speak one of the other. And it's the fault of the leader. It's the leader who should help those people share things. So the leader is someone who works as a mediator and helps people speak one with the other. And finally, take your stakeholders, your supply chain, and create projects with them. Start from small objectives. And then you will have more ambitious objectives. And you will be able to create new joint ventures, new companies. You have no idea. Well, perhaps you have. The power of working together is something incredible. And that is what defines us. We human beings have forged the world because we had the ability to create mental super systems helping us work together. And then the environment. Well, the Earth is a closed mathematical system. The only thing that enters is the solar energy. So whatever we do comes from primary goods that we take from the Earth. And whatever we throw away ends up in our Earth. The planet is a perfect algorithm. However, imagine that you change a variable, and that variable is a cube. Well, there will be a huge impact. So what can a company do? Well, there are four main phases: eco-design, production, consumers, and then recovery and regeneration. And this is what Legor is doing very well. Legor, well, I was very struck by what you do. 100% of your resources come from resources which had already been extracted. Think if all the other companies did the same. So this is a fundamental instrument, and the first step is know yourself and understand all the steps. The life cycle assessment is a very powerful instrument which enables you to understand what is the impact of your product from the mining to the end of life. Why is this so important? On Delphi's monument, this wording is written, know yourself. Well, if you know yourself, you can change things. But if you don't know yourself, you cannot act, you cannot change. In order to change, you have to know yourself, and that's why the LCA is a very powerful instrument. It helps you calculate how much water you use, how much methane you use, how much earth you use for a certain output unit, biodiversity, chemicals, and so on. Think of how much information this can provide. And then eco-design. A product which is well produced is a product which has been well designed. Otherwise, it is a failure. Think of big companies. Think of Apple. Apple is worth more than $3 trillion because they do design work. So they have their own ecosystem. So you have to define what you want. You have to use the LCA instrument because in that way you will have an idea of your impact, and then you have to design the product, but before that you have to design processes. You have to understand all the processes and all the material flows. And finally, you have to involve your supply chain, because you cannot do it alone. You have to involve your supply chain.
La seconda parte è la produzione.
And then production.
Qua penso che lascerò poi la parola all'ospite successivo che
it will be the next speaker who will give you a very accurate idea. Well, one point. Normally, the impact of a company on its product is 10-20%. The remaining 80% of that product comes from their own value chain, from where you take the raw materials. Those who produce semi-finished products, how you use semi-finished products. So that product should be well assembled, but at the end of life, that product, if it has been well assembled, can also be well disassembled, and all the components can go back to the economic circle, and that will save a lot of money and a lot of environment. And then communication and consumption. Well, all that is fine, but if you don't involve your consumers, it's useless. And to do that, well, marketing campaigns are not enough. Everything starts from your sales forces that have to understood why it is important. They had to be involved.
Queste informazioni.
They will have to share this information with the consumers. So sales forces are your touch point, the moment when customers can be influenced. Yesterday I was speaking with some colleagues, and I said that I really miss the local community shop. Why so? Because when I went to those small shops, I had a need, and there was a person who loved their job, and they perfectly knew what to give me. Now I go to Amazon or I go to a big shop and I buy something. Is that really the thing that I need? No. That is to tell you how important it is to involve your sales forces so that they share with consumers, because consumers are responsible and consumers, perhaps when they stop using a certain product, can bring it back to you. And if you did a good job with the design, you can take the product and save a lot of money in terms of supplies. And then recovery, you have to recover things. Imagine if in the IT companies, computers were brought back directly to producers instead of being sent to landfills. And the producer can disassemble the computer. So think of how much you could save. You disassemble, you regenerate, and you recreate. This is a circular economy, which means efficiency from all viewpoints. Circular economy is a way to see consumption. It is a way of working, and as entrepreneurs, we have a responsibility. We need to involve people so that people understand this issue and give them the possibility of trying, of experimenting, of changing the situation. Because if you don't try, in 10 years' time, someone else will do that and will take your market share. So to be leaders in the market also means to take up risks. And in this case, circular economy is not only a question of leadership, it is a question of responsibility. Well, I perfectly remember I was on the Red Sea, and then I went back 10 years after, and there was just one coral and 2 fish. And I'm not saying that we will make it, but it is really criminal not to try it. So to be a B Corp is to take up responsibility, to work together and try. Thank you.
Ringraziamo Matteo Meneghini per la coinvolgente presentazione e ci prepariamo a chiudere.
Thank you very much, Matteo Meneghini. Now we conclude with Gianpietro Zonta, owner of the Dorica limited company, 1989, inspired by the idea to offer something different. He founded Dorica together with his wife, Daniela Raccanello, creating different collections with defined aesthetic canons. That is based on environmental sustainability and respect for people. Please. Thank you very much.
Innanzitutto, buon pomeriggio.
Good evening.
La presentazione iniziale l'ha già fatta, Legor. Allora,
Legor introduced me already. Dorica was created 33 years ago thanks to a synergy combining my wife's experience in different fields of creativity and myself. Right from the start, the objective was that to enhance the skills of people who joined our team by strongly motivating these people and allowing them to work in autonomy. We had common objectives connected with the quality of the product, zero-kilometer supply chain, innovative models by my wife. Dorica becomes a sort of new word, meaning the type of manufacturing that we use. We immediately involved our collaborators and they participate to the profits, and now we gave some shares to 2 collaborators. Now they are members of the company. Now my son and his wife Elena are part of the company, and they are the second generation trying to pursue the company philosophy. Doing business, what is the meaning of that? That means having a mission. The entrepreneur should be motivated by passion, forsightedness, and practice ethical principles. For a period of his or her life, the entrepreneur manages a common good. Therefore, they have a major social responsibility in their community. They can make profits, also for collaborators, and everyone can make life projects for themselves and their families. As you see, we have the benefit company. What are they? Any activity has the objective of sharing profits. Then we have the non-profit sector. Benefit is making profits respecting the environment and people. The third way to business. Dorica is the first company in Italy becoming a benefit company, changing its charters. We are a certified B corporation, a benefit corporation, a B Corp. Here we see the commitment we have undertaken for the environment and social issues. There are areas which are assessed. On the left, the areas to be audited are environment, workers, governance, customers, and community. We have the highest score for the environment, which is the one providing waters, light, air, i.e. all the raw materials which serve to human beings to live. Then we have the workers and then governance. In 17 years, more than 200,000 companies in the world have filled the questionnaire online to become a B Corp company. 2.5% succeeded. There are 6,000 in the world, 200 in Italy. We have our score there, and Patagonia is the most important in the world. We have Illy, Aboca in Italy. Dorica got the certification in 2019 and is the only, unfortunately, single company in the world to have that certification in the jewelry sector. That means sustainability for the environment and the society. That means being transparent, practicing ethical principles, which are part of the company since its start. That was a personal philosophy or thinking, which was then translated into our work. Sustainability is a term which is maybe abused and not very much practiced. Let's try and get a better understanding on that. How can we tell that we practice sustainability if we are not sustainable? We'll see a short clip screened in the National Broadcasting Network Right 2 to show where we are.
Il Congo è grande 8 volte l'Italia.
The size of Congo is 8 times the surface of Italy, richest in terms of raw materials and the prey for China and the US. And the wars are fought for raw materials. I'd like to remind you of some of the sentences we saw in the clip. Congo is rich, but people are poor. When we used to work for white people, they got rich and we just had crumbs. People are afraid of dying when they work, and they are afraid of dying because of hunger when they don't work. What is the meaning of sustainability? That would mean the daily practices connected with ethical values. Our role is a key one because we have two faces. We are producers and consumers. When we are producers of goods and services and we supply the market as employees, entrepreneurs, freelancers, we ask to have an equal pay, an adequate working environments, and working rights. As final consumers, everything is changed. We want to buy a lot with less money. Every day in our life, every cent that we spend is to make the difference between those who continue to work, those who will not work, those who will go on redundancy funds, where people will work, and who will become richer or poorer, where we will go and pollute. The purchasing should be an act of social and environmental responsibility. When I buy something, I do not only do that because I like it or I need it, but because I share its values. How much are these people paid? 2 or 3 euros per day. What are the working conditions of these people? How many hours do they work? And in which conditions? How long can that go on? There are two figures in this type of economy. We have the victims and the persecutors. Who are we? Are our purchases sustainable? Are they responsible? So let's see what Dorica is doing to support sustainability and what is the contribution they give. Too many companies today do greenwashing and very blatantly, and we are cheated, but that goes to our detriment. In the following slides, we'll see all the actions done by the company, sustainability in the products, in the roots, the rediscovery of silk, protection of final consumer with 30 logo, support of young people, and the school of entrepreneurship. This is the synthesis matrix. All we buy in the market, even of high quality, come from supply chains which breach key principles of sustainability in the life cycle. The summation of all these processes and impacts is a major challenge for human beings. We have to reinvent the production and consumption models with a view that one day all products could be reinvented and improved, having sustainability in their DNA. This is a method analyzing what happens in the cycle of different products. The process is analyzed. As you see on the left, we have raw materials, man-made materials, environmental damages, and the needs of human beings. In the upper bar, we have the elements crossed as compared with packaging, transport, use, and end of life. The different colors start from bright red to green red, to bright green. Dorica has a critical point in red, but we have 14 areas, i.e. yellow and green, out of 20, which are in line with the sustainability principle. These are the main results allowing Dorica reach the objective I described. 73% of gold is recycled, 98% is traceable from certified sources, 60% water saved through innovative systems to recover waters, a biodigester to eliminate tensioactive substances. connection with the environment, made in Italy production, collaboration with small workshops in the community, higher wages, plus 20% as compared to the basic salary, which means 40% if we consider the awards which are given for merit, well-being of people, healthy and clean environment, noise abatement, health monitoring, technical parameters, and so on. It's very late, so I'll go very fast. What is this? This is a comparison among 3 B Corp companies in Italy to check whether the product is sustainable. To the left, Dorica, in the center, an apparel company, and then a food company. As you see, we have one critical point, but we have 14 sustainable areas. Just look at the colors of the other 2 companies. Sustainability is in our roots. We discovered silk. That is a project dating back to 2014, and we make items which combine yarns and gold. We discovered that silk is no longer available in Italy. We bought a machine and we made the first silk thread in Europe after 50 years. That was a great emotion because we are not a textile company, but we wanted to have something really made in Italy. A project was started with 3 cooperatives working with disabled people. That was presented by the Veneto region in Europe, and it was awarded by Brussels as one of the best research projects with a view to the development of the primary and secondary sector. My wife makes the first items, necklaces, bracelets, earrings in the company. A project named Treasure is created, which is a rediscovery of a silk in the jewel sector. They are customized. Our project raises considerable interest in Italy and abroad. Television, CNN, BBC got interested in the project. They were fascinated by the idea that silk was back, not in the textile sector, but in the jewelry sector. That was a great opportunity to disseminate our project. The first was done here in the Vicenza Fair. It's a company from Vicenza finding this traditional product. This is the city of Palladio. And at that time, there were silk merchants exporting silk in northern Italy. For centuries, the largest profits made by the Serenissima Republic of Venice were made by silk production. Just think of the northern regions of Italy. The richness they have comes from the production of silk. Treasure is the synthesis of our history. It means rediscovering ancient knowledge. Protection of the final consumers, that is us. JTF is a platform created in 2010. One product out of 4 in the world is a fake. 9 out of them are bought on the internet. JTF is a platform to protect final consumers from forgeries. Usually the price of a forgery is much, much less than the normal price of an original product. Indeed, the features are different in terms of finishings and quality. There are about 100 companies in the world being part of the platform. Have Armani, Diesel, Chopin, Coma, Versace, Missoni, Cavalli. We are the first gold company activating this procedure. You have a code in the buckle, which is laser printed, and by your mobile phone, you can check whether the product is forged or not. We have an agreement with the credit card circuits, and if they buy a forged product, they can be traced and informed that they bought a forged product. Sustainability is supporting young people. Italy is one of the most industrialized countries, the one having the lowest rate of entrepreneurship. Our kids study to find a job, but how many do create a job? Imprendi, that means create a company, is the result of collaboration among entrepreneurs, the University of Padua. One entrepreneur is Roberto Siari from the Friuli region. He has a stock company working in the field of artificial intelligence. The other entrepreneur is myself. I want to tell young people what is the meaning of being an entrepreneur. It's not easy, but you can do that. To have kids making their talent emerge, we look for entrepreneurs, crafts, free professionals devoting their time to children. The Heretical Company. This is a book by Dorica. Why heretical? What is an heresy? It's a free choice against the current, out of the box. This does not tell the story of myself and my wife. There are 12 different heresies, i.e., the way we relate with our employees and in the environment. What is the purpose? Is to disseminate it in schools, the university, and the Imprendi Foundation. And last but not least, thank you very much.
Grazie anche al dottor Zonta per il suo intervento.
Thank you very much. That's all for today. This concludes the 18th edition of JTF. I would like to thank Legor team who has helped me and made this event possible. Fischer Bona as a moderato, Campesato and De Falco for the organization of the meeting. We hope you liked it. The papers will be uploaded on our website, ASAP, and they will be available on YouTube. So thank you very much again. Enjoy the evening and see you on the next JTF. Bye-bye.